Welcome to Math with Professor V. This is part 2 of the video solving 100 questions on everything to do with sequences and series. If you haven't checked out part 1, it is linked in the description. And just as a heads up so that this video isn't 20 hours long, as I solve the remaining questions, I'm just going to explain my work as I go, but I'm not going to give too much of a background lecture before each topic. So if you need any in-depth explanations or you've forgotten stuff, then I have all of the full-length video lectures corresponding to all the topics with this unit on sequences and series linked in the description. So just go there to fill in any gaps that might be needing filling, you know what I mean? So here we go though, picking up where we left off, question 53. Use the ratio test to determine if the series converges or diverges. So first let's identify what a sub n is. A sub n is n factorial times e to the negative 8n, but you know what? I like thinking of it as over e to the 8n better. And then now let's go ahead and apply the ratio test. So we're going to take the limit n approaches infinity of the absolute value of a sub n plus 1 over a sub n. So this is going to give us the limit n approaches infinity, absolute value. A sub n plus 1 is going to be n plus 1 factorial over e raised to the 8 times n plus 1. And then I'm going to divide all of this by a sub n, which is n factorial over e raised to the 8n. Good? Now notice here, nothing's going to be negative, so I don't need to keep the absolute value bars. I can just dump them and then start simplifying. And when I do the ratio test, I don't really write out a sub n in the denominator. I already start multiplying by its reciprocal just to save some steps and time. So we have now n plus 1 factorial over, and then let me distribute out that 8 now. So this is e to the 8n plus 8 times e to the 8n over n factorial. Good? Okay, and then you want to break down n plus 1 factorial. You always break down the larger factorial quantity so I can cancel with the n factorial that's on the other side. So when deciding which one to break down between the two, you break down the larger one and just start listing out the terms. So n plus 1 factorial, that's n plus 1 times n factorial. If you need a recap on factorials, I have a cool video on it in the description. And then using our laws of exponents, I can also break up e raised to the 8n plus 8, because that's e to the 8n times e to the 8th, like that. Okay, perfect. And then now we're ready for all the canceling fun. This is honestly my favorite part. So n factorial, gone. E to the 8n, also gone. And then now we're just left with the limit. As n approaches infinity, we have n plus 1 over e to the 8th. Now, e to the 8th is just a constant, so it's not changing as n approaches infinity, but n plus 1 in the numerator, that's definitely all going to infinity. So infinity divided by some constant, I don't even care what it is, it's still going to go to infinity. And then we did the ratio test right now. So what I need to do anytime I find this limit is compare it to 1. Infinity is most definitely greater than 1. So then that tells me that my series diverges. And just rewrite it. The sum n equals 1 to infinity of n factorial times e to the negative 8n diverges. I'm going to put by the ratio test. I always put what test I used. This time they told us what test to use, but just it's a good habit to have. Okay? Good. I got more for you. I got more. Don't you fret. All right, next one we have the sum n equals 1 to infinity of n to the 10th over 10 to the n. So let's just jump right in. Limit n goes to infinity, absolute value. A sub n plus 1 is going to be n plus 1 to the 10th over 10 raised to the n plus 1. And then divided by a sub n, I'm already going to multiply by the reciprocal. So times 10 to the n over n to the 10th. Again, I don't need to keep the absolute value bar, so I'm not going to write them anymore. So limit n goes to infinity. Now, this is another slick little maneuver you have to use. N plus 1 is to the 10th, and so is n. Nothing's going to cancel, but I'm just going to group them together in the same set of parentheses because they're both raised to the same power, the 10th power. And then now I'm going to break up 10 to the n plus 1 and write it as 10 to the n times 10 to the first. And then this 10 to the n stays in the numerator. Are we good? Okay, this is perfect. So 10 to the n will cancel. And then I can rewrite all of this because this is n over n plus 1 over n, right? So then now we have the limit as n approaches infinity of 1 plus 1 over n to the 10th times, this is just 1/10. So now as n goes to infinity, 1 over n, that's going to go to 0. So I have 1 plus 0, that's just 1, raised to the 10th, that's still 1. So this limit is 1 times 1/10, which is 1/10. And what do I care about this limit? Well, we're doing the ratio test. So all I'm interested in is whether or not it's less than or greater than 1. This is less than 1. So then that tells me that the sum, n equals 1 to infinity, of n to the 10th over 10 to the n converges by the ratio test. Perfect. All right, another one. Use the ratio test to determine if the series converges or diverges. All right, anytime you see factorials, you're going to use the ratio test. I honestly would be hard-pressed to think of a scenario where I wouldn't use it, okay? So absolute value, a sub n plus 1, be careful. This 2n factorial, put n plus 1 in parentheses, all right? Because we're going to have to distribute the 2 through. And then you have 9 to the n plus 1, and then n plus 1 factorial. That's all of a sub n plus 1. Divided by a sub n, so I'm going to multiply by the reciprocal of a sub n, 9 to the n, n factorial over 2n factorial. Are we all right? Okay, good. Now, 2 times n plus 1 becomes 2n plus 2. So I have factorial of all of that. If you forgot to put the parentheses around the n, then you might accidentally have 2n plus 1, and that would mess up your whole answer. I know. You would actually get the wrong result. So be careful. Limit n goes to infinity. Again, I don't need absolute value. Nothing's going to be negative, so I'll just dump them, okay? And then we've got now 2n plus 2 factorial here, n factorial, n plus 1 factorial, 2n factorial. I'm going to try to get these guys to cancel. Let me break down the bigger one. And then I'm also going to try to get these guys to cancel. Let me break down the bigger one. So 2n plus 2 factorial, that's 2n plus 2 times 2n plus 1 times, and then now I'm just going to stop at 2n factorial since I see it on the denominator over here and I know it'll cancel. And then 9 to the n plus 1, I can break that down. That's 9 to the n times 9 to the first. N plus 1 factorial, let's break that down. That's n plus 1 times n factorial. So all of that's broken down. And then here, these guys, I'm going to leave them as is because they're ready to cancel. Okay, and then you can throw a cancel party. It's so satisfying just to cross a bunch of stuff out. It somewhat reminds me like when you play Tetris. 9 to the n is gone. There's something else, but let me show you in the next step. So let's see who didn't get canceled out. Limit n goes to infinity. In the numerator, I have 2n plus 2 and 2n plus 1. But you know, this 2n plus 2, I can take a 2 out. Then it's n plus 1 times 2n plus 1 over, this is 9 times n plus 1, yeah? Aha, you see how n plus 1 cancels again? That was a bonus. Ugh, extra fun. So then limit n goes to infinity, 2n plus 1, oh, times another 2. You know what? Let's just distribute it through. 2 times 2n plus 1, I'll just write 4n plus 2 over 9. N is going to infinity, so the numerator is going to infinity. The denominator is just some positive constant, so everything's still going to go to positive infinity, which is greater than 1. And we are done. So that tells me the sum, n equals 1 to infinity, of 2n factorial over 9 to the n times n factorial diverges by the ratio test. Very good. Okay, more factorial fun. I want you to see like as many possible scenarios. Sum n equals 1 to infinity, 5 times n factorial squared over 2n factorial. Don't be intimidated by the fact that we have a factorial squared. If it helps you, just think that means you have n factorial there twice. If you want to write it out twice, if it makes you feel better, I would do that. So limit n goes to infinity, we have absolute value 5 times n plus 1 factorial. I could write it squared or I could just write it out twice, okay? Either way, whatever you're comfortable with. And then in the denominator, we have 2 times n plus 1 in parentheses. Don't forget that, factorial. And then I'm just going to multiply by the reciprocal of a sub n. So 2n factorial. And then this is going to be 5n factorial squared, or I can just write it out twice, whatever you want. Okay. Again, I don't need to keep absolute value, so let's start seeing what we can simplify and break down. Here is 2 times n plus 1 factorial, so that's really 2n plus 2 factorial. This one I'm going to break down because it's larger than 2n factorial, so this one will get broken down to cancel. And then each of these will get broken down so I can cancel with the n factorial there. And then you know what? Just cancel the 5 now. Get out of here, 5. Okay. So n plus 1 factorial, n plus 1, n factorial. I got 2 of them. So you could put squared or write it out twice. And then 2n plus 2 factorial in the denominator, that's going to be 2n plus 2 times 2n plus 1 times 2n factorial. So everything here now is broken down, ready for canceling fun. And then 2n factorial up here over n factorial, n factorial. Okay, cancel party time. N factorial, gone. Another one, gone. 2n factorial, gone. There is one more thing we can do, but let's just write it out carefully. Limit n goes to infinity, n plus 1 times n plus 1 over, this is just like that last problem. You can take a 2 out, and then you have n plus 1, and then 2n plus 1 is the other factor. So n plus 1 cancels, and then we should be ready to take the limit. So limit n goes to infinity, n plus 1 over, let me distribute, that's 4n plus 2. Divide by the highest power of n in the denominator. So let me divide by n to the first. Remember, no L'Hopital's rule when we're working with the terms of a sequence or series. They're not differentiable. So we'll have 1 plus 1 over n up top, 4 plus 2 over n in the bottom. N goes to infinity, so both 1 over n and 2 over n go to 0. And then this is 1/4. I just did ratio test, so I always compare this limit to 1. 1/4 is less than 1. So that tells me that the sum, n equals 1 to infinity of 5 times n factorial squared over 2n factorial converges, since the limit was less than 1, by the ratio test. Good? Notice all of these limits have come out to be less than 1 or greater than 1 because we were told to do the ratio test. If you ever get that the limit is 1, the ratio test is inconclusive. It gives you no information. It means you should have used a different test. It was the wrong time to use the ratio test. So if this ever comes out to be equal to 1, it's a U problem. Pick a different test, okay? Now we're going to use the root test to determine if the series converges or diverges. So root test is very similar to the ratio test. It's just instead you take the limit as n goes to infinity of the nth root of the absolute value of a sub n, hence its name. So now we have limit n goes to infinity, nth root of the absolute value of n factorial to the n over n to the n to the 10th. Okay. Now remember, when you take the nth root of something, that's the same as raising it to the 1 over n. I don't know if you need to write that out and remind yourself or if you've got it under control. Also, like nothing's negative, so I'm not going to keep writing absolute value. So here we have n factorial to the n over, and then remember your laws of exponents. When you have a power raised to another power, you multiply those exponents. So n to the 10n. And then this is all being raised to the 1 over n. That means the same thing as taking the nth root, raising to the 1 over n. So I'm going to distribute that exponent through to the numerator and denominator. And n and 1 over n just cancel up top. So then you just have the limit as n goes to infinity of n factorial over, and then here if I take 10n, divide it by n, it's just going to be 10. Okay? Now, intuitively, you could probably figure out this limit is going to go to infinity because you only have 10 factors of n down here where you can have much more than 10 in the numerator as n approaches infinity. However, if you need to prove it a little bit more rigorously, you can work with some inequality to show that this is going to go to infinity. It's a little, I don't love doing that. And another option that you have is you could actually apply the ratio test for sequences, not for series, just to investigate where is this going, okay? So if you haven't ever heard of the ratio test for sequences, that's not surprising to me because not every textbook covers it, but it's basically the same as the ratio test when working with the series. It tells you where the terms are going, okay? And I have a whole video on it. So if you've never heard of it before and you just want like a little quick recap, go check it out. It's linked in the description. But now we can go ahead and apply the ratio test for sequences to determine what the limit is of n factorial over n to the 10th. So we're going to say, let's consider the limit as n goes to infinity of n plus 1 factorial over n plus 1 to the 10th divided by a sub n or multiplied by n to the 10th over n factorial. And then again, see, once it starts getting repetitive, you're like, I'm in business. Bring on that final exam. These are both raised to the 10th. So I'm going to group them together to take this limit n goes to infinity. This is n over n plus 1 to the 10th. And then I have n plus 1 factorial. Let me break that down. That's n plus 1 times n factorial over n factorial down here. Okay, so these are gone. Now, how would you work with this limit? Just focus on the inside. I can't split the denominator the way I did in the previous problem because we have two terms here, but I'm going to divide everybody by n. So divide by n, everybody, okay? Then this is the limit. N goes to infinity, 1 over 1 plus 1 over n to the 10th. And then I have times n plus 1. So if n goes to infinity, this 1 over n is going to 0. This is just 1 now to the 10th, so that's 1, times n's going to infinity, so this is going to infinity. So this is 1 times infinity, which is approaching infinity. What does that tell me then? That this limit now, the limit of n factorial over n to the 10th is infinity. So then, at long last, I can say, well, I just did the root test. And if this limit is greater than 1, then that tells me that my original sum Who was it? It was the sum n equals 1 to infinity, n factorial to the n over n to the n to the 10th diverges by the root test. The test that I applied for the series was the root test. Along the way, when trying to find this limit, I used the ratio test for sequences. That's not a very common topic that comes up, but I just wanted to cover it in case it's in your book and in your curriculum. Okay, let's look at another one. And again, we're using the root test. We have here the sum n equals 1 to infinity, natural log of n over 9n plus 1, all raised to the n. Now, even if they hadn't told me to do the root test, I'd be inclined to apply it because everything's being raised to the n. So it feels like everything should work out nicely, you know what I mean? So we've got the limit, n goes to infinity, nth root of absolute value of natural log of n over 9n plus 1, all raised to the n. Okay, so these n's cancel out. And then n is going from 1 to infinity. In this limit, like natural log isn't going to be negative, neither is this, so I don't need to keep the absolute value. So we've got limit, n goes to infinity, natural log of n over 9n plus 1. All right, so as n gets very, very large, natural log of n goes to infinity, so does 9n plus 1. So we have an indeterminate form of the type infinity over infinity. But remember, we can't just go ahead and apply L'Hopital's rule because this is not a differentiable function. So we have to, like, off to the side, go, hey, consider the limit as x goes to infinity of the natural log of x over 9x plus 1. So you literally just swap out your n's for x's. And it might feel silly, but it's important to show that you understand when you're allowed to apply L'Hopital's rule, okay? So yes, we have indeterminate form of the type infinity over infinity. Now we can go ahead and do it. So limit x goes to infinity, derivative of the numerator of ln of x is 1 over x. And then derivative of denominator is just 9. So this is the limit. X is approaching infinity, 1 over 9x. That's 0. So then that tells me this limit here is 0. And I just applied the root test. So I always compare that limit to 1. 0 is definitely less than 1. And then that tells me that the sum, n equals 1 to infinity, natural log of n over 9n plus 1 to the n converges by the root test. Good? Okay. More root test fun. You guys, like I said, we got 100 questions total here. Another one. So limit n goes to infinity, nth root of absolute value of n raised to the n over 7n squared. 7 raised to the n squared, excuse me. Okay, again, I don't need to keep the absolute value bars. And then remember, taking the nth root is the same as raising something to the 1 over n. So you have n to the n over 7 raised to the n squared. Each of these gets raised to the 1 over n, to the 1 over n. So here, when I simplify, I multiply these exponents, they just cancel. So this is limit, n goes to infinity, just n up top. And then down here, you've got n squared times 1 over n. So one of the n's is going to cancel, but I still will have 7 raised to the n there. And then again, n's going to infinity. So this is going to infinity, denominator is going to infinity, which is an indeterminate form. However, yeah, before we apply L'Hopital's rule, we have to just do a little consider the limit as x approaches infinity of x over 7 to the x. So once you've confirmed or verified you have an indeterminate form of the type infinity over infinity, or 0 over 0. That's the only time you're allowed to apply L'Hopital's rule. If you forgot some stuff about L'Hopital's rule, don't worry. I have a video linked in the description. I have a video for everything pretty much, guys. Let's go ahead and apply it. So limit x approaches infinity. Derivative of the numerator, derivative of x is just 1. And then derivative of 7 to the x. Derivative of a to the x is a to the x times ln of a. So this is going to be 7 to the x times ln of 7. Did you forget that derivative? It doesn't happen that often. A to the x is a to the x times ln of a. When the base is e, ln of e is 1, so you don't see that. Okay. Anyways, no matter how you slice or dice it, the denominator is going to infinity now, and the numerator is just a constant, so this is 0. Good. So then that tells me, all right, this limit that I was looking at earlier, that's 0, which is less than 1. And then now I can say, all right, that means the sum, n equals 1 to infinity, n to the n, over 7 to the n squared converges by the root test. Good. How was that? I have three more root tests for you guys. Oh yeah, we're going to be pros by the end of this video. Use the root test to determine if the series converges or diverges. Okay, so we've got the limit, n goes to infinity, nth root of absolute value, n over n to the 1 over n plus 10 to the n. So then this is going to be the limit, n approaches infinity. Now there's nothing here for this nth root to cancel with. So I still have nth root of n up top. I'm going to write it as n to the 1 over n instead. And then this nth root will cancel with the n power exponent right there. So then I just have n to the 1 over n plus 10. Okay, now as n goes to infinity, you have to be really, really careful with n to the 1 over n. I know, the limit as n goes to infinity of n to the 1 over n, it's an indeterminate form because this base is approaching infinity and this exponent is approaching 0. And infinity raised to the 0 is an indeterminate form. There's 7 indeterminate forms. This is one of them. Infinity to the 0, it can be 1, but not always. And so don't take it for granted. It needs to be investigated further. So how do we do it? Well, we are going to use L'Hopital's rule, but remember L'Hopital's rule can only be used when your indeterminate form is a fraction and it's either infinity over infinity or 0 over 0. So when you have an indeterminate power, there's 3 of them, we have to take a natural log of whatever we're taking the limit of so we can move the exponent and make a fraction. So if you forgot how to do this, it's okay. I explained it in that L'Hopital's rule video. So what we're going to do now is consider the limit. And I can't use n's, remember, because we need a differentiable function. So I'm just going to consider the limit as x approaches infinity of, let me already add the natural log of x to the 1 over x. All right, so I switched all my n's to x's and I added a natural log. And I'm only taking the limit of this part. Once I figure out what the limit is, then I'll plop it back in the original problem, okay? But I don't want to work with this whole messy stuff. Move the 1 over x to the front. So then now this is limit, x goes to infinity, 1 over x times ln of x. And you're basically where you need to be to apply L'Hopital's rule. Just rewrite it cuter. Write it as limit x goes to infinity, ln of x over x. Perfect. So then, yep, always verify you have either infinity over infinity or 0 over 0, which we do. So then now we can use L'Hopital's rule. Always write down that's what you're doing. And then we've got limit, x goes to infinity. Derivative of ln of x is 1 over x. And then derivative of x is 1. So this is the limit as x approaches infinity of 1 over x, which is 0. Now, this is the limit of the natural log of x to the 1 over x. if I wanted the limit without the natural log, if I wanted the limit as x goes to infinity of just x to the 1 over x, well, then I would have to take e and raise it to whatever I got, in this case, the 0, which is 1. Because basically, if I take e and raise it to this limit and I pass e through, then e and ln cancel. And you don't have to write all that out, but I show it in the video if you forgot the nuances of what's going on behind the scenes. But at the end of the day, then we can say, all right, this tells me that the limit as n approaches infinity of n to the 1 over n, it is 1. Okay, so this time, infinity to the 0, our indeterminate form for this problem did come out to be 1, but please believe there's other times it is not 1, so it's not a waste of time to do this. In fact, it's crucial that you do it, okay? All right. So what can I do now? I can plop in 1s for both these guys. That's going to 1, that's going to 1. And then I can say my limit is 1 over 1 plus 10, which is 11. 1 over 11, that's less than 1. So then that tells me my sum, n equals 1 to infinity of n over n to the 1 over n plus 10 to the n. What does it do? It converges, yes, by the root test. Very good. Very good. Here we go, 61. Root test again. So we'll take the limit, n goes to infinity, nth root of absolute value, 6n to the 1 over n minus 1 over 3n to the 1 over n minus 1, all raised to the n. Okay, this time everything's being raised to the n, so it just cancels really nicely when we take the nth root. Oh, I forgot the other absolute value bar. Well, I'm going to drop it in a hot second anyways because nobody's negative, so we don't need them. So we have limit n goes to infinity, 6n to the 1 over n minus 1 over 3n to the 1 over n minus 1. And then, here's that indeterminate form back to haunt us, n to the 1 over n. Now, we literally just did this a minute ago, so I'm going to say they both go to 1, see above. I personally have no problem if my students cite their own work on an exam. Like if they do something in problem 7 and they need to reference something they did in problem 3, I'm cool with that. So I don't need them to rewrite step by step what they just did a second ago. But make sure you don't do anything that it's going to cause you to lose points, okay? Good. So then I can just say this is what? 6 minus 1, so 5, over 3 minus 1, which is 2. 5 halves, that's greater than 1. So then that tells me the sum, n equals 1 to infinity, 6n to the 1 over n minus 1 over 3n to the 1 over n minus 1, all raised to the n, diverges by the root test. Okay, good. Already having that limit worked out made this one really easy. Last one. You know, this should have been the first one. It's so easy. So again, root test. Let's look at the limit. N goes to infinity, nth root of absolute value, 1 over n squared minus 1 over n to the 5th to the n. N's cancel. Then this is limit, n goes to infinity. I don't need absolute value, nobody's negative. 1 over n squared minus 1 over n to the 5th. This goes to 0. This goes to 0. This is 0, which is less than 1. So then that tells me that the series does what? If the limit's less than 1, then I say it converges by the root test. Okay, good job. Easy, right? Okay, now we're going to get into the idea of absolute versus conditional convergence. So we're going to determine if the series converges absolutely, if it just plain old converges, aka converges conditionally, or if it diverges. Now, if you haven't watched my video on absolute versus conditional convergence, I really recommend that you do so because I have like a nice little flow chart that helps you organize your strategy when solving problems like this. Also, keep in mind, if you do the ratio or the root test, they're all or nothing. So either the series converges absolutely or it diverges. You don't need to check for conditional convergence. But if you use any other test and the series doesn't converge absolutely, then you have to check for conditional convergence. And you always use AST when checking for conditional convergence. Okay? But that's a lot. Watch the video if this is like a topic that's a little sticky for you. Okay? First, always test for absolute convergence, unless you can tell it's going to diverge. Then you can jump straight there. So I'm going to test for absolute convergence. I'm going to look first at the absolute value of an. So absolute value of -1 to the n over 9n to the 1/4 plus 1. All that happens is that alternating term goes away. So this is 1 over 9n to the 1/4 plus 1. So it's up to us. We can pick any test we want to investigate whether the sum of 1 over 9n to the 1/4 plus 1 converges or diverges. You can pick any test. So you can say, let me see if it is telescoping, though I wouldn't really ever use that one unless I was forced to. Integral test, we could do comparison or limit comparison test. You could do not AST because we're testing for absolute convergence, so we don't have an alternating series. You could do ratio test, you could do root test. Most of the time, you're going to do limit comparison test, okay? Or you might right off the bat be able to say it's a p-series or geometric. This one is definitely giving me p-series vibes, so I'm going to go for limit comparison test. Looking at the highest power of n, there's no n's in the numerator and just n to the 1/4 in the denominator. So I'm going to say, okay, consider bn, which is 1 over n to the 1/4. And I know the sum, n equals 1 to infinity, of 1 over n to the 1/4 is a p-series. P equal to 1/4, which is less than 1. So this series diverges. So let me use a limit comparison test because I feel like my series will diverge as well. And I'm going to look at the limit as n approaches infinity of 1 over 9n to the 1/4 plus 1 over b sub n, which is 1 over n to the 1/4. Okay, now I'm going to warn you about something, and I warned you about it earlier. You have to write this step out. That's your justification when applying limit comparison test. And don't just write out bn. Bn is not a series. You have to write sigma in order to tell me what this p series is doing. Series has a sigma. All right, next step. Let's clean up so we can take the limit. N goes to infinity. I'm going to have n to the 1/4 up top now, over 9n to the 1/4 plus 1. And then divide by the highest power of n in the denominator, which is n to the 1/4. And let's see, we've got now limit, n goes to infinity, 1 over 9 plus 1 over n to the 1/4. So as n gets very, very large, this term goes to 0. I'm just left with 1 over 9. And no, I'm not comparing it to 1. I only do that for ratio and root test. For limit comparison test, all I care is whether or not this number is finite and non-zero, which it is. Finite and non-zero. And then what that tells me is my series behaves the same. Where was my series? The sum of this without the alternating term, he behaves the same as whatever I compared it to, this divergent p-series. So this tells me that the sum, n equals 1 to infinity, no alternating part because we're looking for absolute convergence right now. So the OG without the alternating part, it also diverges by the limit comparison test. Okay. So what does that tell me? That tells me then that the original sum, n equals 1 to infinity, of -1 to the n over 9n to the 1/4 plus 1 does not converge absolutely. So are we done? No, because now we need to check, does it converge conditionally? So I need some space. Let's do it. But does it converge conditionally? When testing for conditional convergence, you always use AST. Always and forever. Use AST. So now I want to look the absolute value of a sub n is 1 over 9n to the 1/4 plus 1. That's what we call b sub n when we do AST. It's kind of confusing because then like here was this other b sub n for limit comparison test, but that's basically what we're going to look at here. I'm going to see whether 1 over 9n to the 1/4 plus 1 satisfies the two conditions of the AST. So I'll just rewrite. And now b sub n is this guy, 1 over 9n to the 1/4 plus 1. And we check two things. First, I check, is b sub n decreasing? Well, just by the definition, it's clear that it is, right? So b sub n plus 1 is 1 over 9 times n plus 1 to the 1/4 plus 1. And since this denominator is definitely bigger than this one, I can say for sure this is less than 1 over 9n to the 1/4 plus 1, which is b sub n. So I just showed b sub n plus 1 is less than b sub n. That's decreasing. And then the second thing I want to check is what's the limit as n goes to infinity of b sub n. Well, the denominator is getting very, very large. Numerator's constant, so it's 0. So perfect. Both conditions of AST are satisfied. So then that tells me the sum, n equals 1 to infinity, of negative 1 to the n times 1 over 9n to the 1/4 plus 1 converges by the alternating series test. And then to answer the original question at hand, that tells me that the sum, n equals 1 to infinity, negative 1 to the n, 1 over 9n to the 1/4 plus 1, it converges conditionally. So of the three options, converging absolutely, converging conditionally, or diverging, this one converges conditionally. On the condition that it is an alternating series. Exactly. Okay. Here we go. We have same question. So absolute conditional convergence, or is it divergent? So we have the sum n equals 1 to infinity, negative 1 to the n times natural log of 9n plus 2 over 8n plus 1. Now this one, I'm not even going to check if it converges absolutely. I'm not even going to do AST because I'm looking here at the terms and these don't go to 0. No, they don't. As n gets really, really large, do you know where it's going? The limit as n goes to infinity of the natural log of 9n plus 2 over 8n plus 1. If you want to divide in here everybody by n, or maybe you can just tell by looking, yeah? So the limit as n goes to infinity, natural log 9 plus 2 over n over 8 plus 1 over n. These guys go to 0, 0. This limit is ln 9 over 8. And that's not 0. So this would fail AST. And not only that, I can just jump straight right now. I don't even have to waste my time doing AST and say, hey, it's going to fail the test for divergence. Because it's alternating, all the even terms, when n is an even number, they're going to be positive and they're going to approach positive ln 9/8. And then the odd terms are going to have a minus sign and they're going to approach negative ln 9/8. So then the limit of the terms doesn't exist. So let me state this out very properly. So this means the limit as n goes to infinity of negative 1 to the n natural log 9n plus 2 over 8n plus 1 does not exist because the even terms approach positive ln 9/8, and the odd terms approach negative ln 9/8. And if the limit doesn't exist, then definitely that limit's not 0. And now what test am I referring to or referencing? The test for divergence. If the terms don't go to 0, then that tells me my series, I don't feel like saying it, I just wrote it, diverges by the test for divergence. Test for divergence, okay? So you can just jump straight to that and we're done. I don't have to waste my time looking at absolute convergence, then trying AST, blah, blah, blah. The terms didn't even go to 0, so no chance of converging. Moving on with our lives. Next. I feel like Ariana Grande. Next, we have the sum, n equals 1 to infinity, -6 to the negative n. So first let's test for absolute convergence. So let me look at the absolute value of an. So that would be the absolute value of -6 to the negative n. So first, let me not even worry about the absolute value. Let's rewrite this with a positive exponent. So something raised to a negative exponent means you have 1 over that something to a positive exponent. Yes? Okay, good. Then when I make everything positive, now the -6 becomes a +6. So then this is just 1/6 all raised to the n, right? I could throw the 1 in there. Oh, but wait a minute. These are the terms of a geometric series. It's geometric. Can you identify what R is? R is 1/6, and the absolute value of R is less than 1. So that tells me the sum, n equals 1 to infinity, of 1/6 to the n converges. And remember, this was the absolute value of the original terms of my series. So now I can say, oh, my original series, that guy converges absolutely. Converges absolutely. And we're done, because absolute convergence is the strongest type of convergence. So you don't need to do AST. You don't need to waste precious seconds of your life that you'll never get back. You just say, I'm done. In fact, let's box it. That's how done we are. And we're moving on with our lives, okay? Beautiful. Here's another one. The sum, n equals 1 to infinity, -1 to the n times the square root of n squared plus 1 minus n. Okay. So first, let's test for absolute convergence. Oh yeah, here we go. So the absolute value of an is going to be absolute value -1 to the n times the square root of n squared plus 1 minus n. So that -1 to the n is going to go away. And then I just have square root n squared plus 1 minus n. Now, I want to get an idea what this thing's doing, because I mean, if it doesn't even go to 0, then like the last problem, I can be done, or like 2 problems ago, I could be done very quickly. It would fail the test for divergence. But that's not what's happening here. As n goes to infinity, this is going to infinity, minus this does too, which is an indeterminate form. And so I'm having a hard time really figuring out what the heck is going on. So instead, why don't we go ahead and rewrite the absolute value of a sub n so that we can see where the terms are going. We can look at the limit a little bit better. And I'm going to multiply top and bottom by the conjugate of what I see right there. So the conjugate would be the square root of n squared plus 1 plus n. And I'm going to do that top and bottom. That way I'm just multiplying by 1, right? I'm not doing anything illegal. So then now I have n squared plus 1, because rad n squared plus 1 times rad n squared plus 1, the radical goes away, minus, this is just n squared. And then down here we have square root n squared plus 1 plus n. So then now this is 1 over square root n squared plus 1 plus n. This is absolute value of a sub n. And now I feel a little bit better because I can get a better feel, right, for how it's behaving. So first of all, as n goes to infinity, this is going to 0. So test for divergence won't work. Remember, test for divergence will only tell you that a series diverges when the terms of the series don't approach 0. These guys go to 0, so I have no information. However, I'm looking and I'm kind of getting the feeling like we can do a limit comparison again because this is behaving somewhat like a p-series. Who should I compare it to? This part is crucial. If you choose the wrong p-series, your limit comparison test will be inconclusive. Pick the highest power of n in the denominator. But that's not actually going to be n squared because you see how my n squared is underneath the square root? Yeah. So square root of n squared, technically it's absolute value of n, but because when we're talking with sequences in series, n's always positive going to infinity, we don't have to worry about absolute value. So I'm going to go ahead and do limit comparison test. And if I'm going to compare it with a series, I'm going to choose the sum n equals 1 to infinity, 1 over n. Because n to the first, that's the highest power that I see down there. And the sum n equals 1 to infinity, 1 over n, you should know this series. This is the harmonic series. And what does the harmonic series do? It diverges. Okay, so that tells me this guy probably is going to diverge. Let's prove it using the limit comparison test. So let's consider the limit as n goes to infinity, 1 over square root of n squared plus 1 plus n over 1 over n. So this is now limit n goes to infinity, n over square root n squared plus 1 plus n. Now to evaluate the limit, I'm going to divide by the highest power of n in the denominator, which we all agreed was n to the first a second ago. And then we actually did a very similar limit problem in part 1 of the video. It was with a sequence, but same thing. So when this n comes underneath the radical, it becomes n squared. So then I have 1 plus 1 over n squared plus 1. If that step's confusing, then go back watch part 1 of the video where I do a limit problem like this early on. Okay. That's good. That's good. So this is going to go to 0. I have 1 over square root of 1 plus 1. So this is 1/2. What do I care about 1/2? Just that it's finite and not 0. And then that tells me my series, the absolute value of this, does the same thing that the harmonic series does. Well, the harmonic series is a divergent series. So this tells me the sum, n equals 1 to infinity, square root n squared plus 1 minus n, also diverges by the limit comparison test. So then that means the sum, n equals 1 to infinity, negative 1 to the n, times the square root n squared plus 1 minus n does not converge absolutely. Because when I took the absolute value and I did limit comparison test, it diverged. Okay, but we're not done. Because now I have to check, does it converge conditionally? So what test do I use for conditional convergence? Do you remember? Yes, AST, always and forever, AST. So who is B sub n when we use AST? Everything without the alternating part. So B sub n is square root n squared plus 1 minus n. And we check two things. One, that Bn is decreasing. Well, you know what? To check decreasing, it's honestly easier if we work with the other version of Bn that we had right here. And to take the limit. So why don't we just work with that instead? I'm going to say, hey, we also have an alternate version of B sub n that I like working with better. 1 over rad n squared plus 1 plus n. Okay, so now let's see. What's B sub n plus 1? Replacing all of the n's with n plus 1, we have 1 over square root n plus 1 squared plus 1 plus n plus 1. And what happened? The denominator just got bigger. So if the denominator is bigger, then for sure I can say now it's smaller than what I had a second ago, 1 over rad n squared plus 1 plus n, which is b sub n. So yes, b sub n is decreasing. And then the second thing I need to check is what's the limit as n goes to infinity of b sub n. Well, that's crooked. There we go. 1 over rad n squared plus 1 plus n. I mean, hopefully it's clear. This is all going to infinity. I have a constant in the numerator. That's 0. So we're good. So now I can say the sum n equals 1 to infinity, negative 1 to the n. Let me write it the way they gave it to me, not after we multiplied by the conjugate. This series converges by the alternating series test. So then what can I say in response to the original question that was posed? Well, then the sum n equals 1 to infinity, negative 1 to the n, rad n squared plus 1 minus n, converges conditionally. Okay. These are a lot of work. I don't put more than one or two absolute or conditional convergence questions on the test where they have to do the full thing out. Okay, I got another one for you. Oh yeah. We have the sum n equals 1 to infinity, negative 1 to the n times 3n to the 4th plus 6 over 8n to the 6th plus 9. So here's a sub n. Absolute value of a sub n will get rid of the alternating part, and then I just have 3n to the 4th plus 6 over 8n to the 6th plus 9. So now I want to know, what is the sum n equals 1 to infinity of this guy doing? Is it convergent or divergent? I'm going to try to use limit comparison test again, but who should I compare it to? Well, look at the highest power of n in the numerator. It's n to the 4th. Look at the highest power of n in the denominator. It's n to the 6th. That simplifies to 1 over n squared, right? And what do I know about the sum n equals 1 to infinity of 1 over n squared? Well, that's a p series. P is equal to 2, which is greater than 1. So this series converges. So most likely this series will converge also, but let's prove it. Let's go ahead and use the limit comparison test. So now we're going to consider the limit as n goes to infinity, 3n to the 4th plus 6 over 8n to the 6th plus 9 over 1 over n squared. So this is the limit. N goes to infinity. This n squared is going to come multiply up in the numerator. Let me distribute it all at once. Are you okay with me doing that? 3n to the 6th plus 6n squared over 8n to the 6th plus 9. And then to take this limit, we'll divide by highest power of n from the denominator, which is n to the 6th. And then we get the limit as n approaches infinity of 3 plus 6 over n to the 4th over 8 plus 9 over n to the 6th. And then 6 over n to the 4th, that's going to go to 0. 9 over n to the 6th, that also goes to 0. So then we just have 3 over 8 left over. Perfect. What do I care about this limit? I just did limit comparison test. So all that matters is that it's finite and not 0. Boom. So then that tells me that my series does the same thing as the one that I compared it to. Who did I compare it to? Do you remember? Yes, I compared it to this convergent P series right here. So then my series and that series are twinsies. My series also converges by the limit comparison test. So then now what can I say about the original series that I had before I took the absolute value, the one that was alternating? Well, when I took the absolute value, it converged. So that means this original series converges absolutely. That's the strongest kind of convergence. So do I need to sit there and go do alternating series test? No, I'm done. I just showed that it has the strongest type of convergence. So don't waste your time. That's why you always want to check for absolute convergence first, because if you can show that the series converges absolutely, then we're done. One and done. I love it. Okay, here's another one. We have the, again, same question. Converges absolutely, conditionally, or diverges. 68. We have the sum n equals 1 to infinity, negative 1 to the n times n factorial squared times 8 to the n over 2n plus 1 factorial. Now, as soon as I see factorial, my mind goes, ooh, I should do the ratio test. And the cool thing about the ratio test is it's all or nothing. Either the series converges absolutely when you do ratio test or it diverges. That's it. You don't need to waste your time doing AST ever. Okay? Great. So let's go ahead. Now we're ratio test pros. Limit n goes to infinity. Absolute value a sub n plus 1 is going to be negative 1 to the n plus 1. Now you're not scared of n factorial squared, so I'm just going to write n plus 1 factorial squared, 8 to the n plus 1 over, ooh, please be careful here, 2 times n plus 1 in parentheses plus 1 factorial. Are we good? Times, yes, I'm already going to multiply by the reciprocal. So we're going to have up here 2n plus 1 factorial over negative 1 to the n factorial squared, and then 8 to the n. Good? Great. Okay, here's the cool thing. When you do ratio test or even root test and you have these alternating series, if I take the absolute value of negative 1 raised to some power, it's going to make it positive 1, and we don't need to write it anymore. So that's great. And then nothing else is going to be negative, so I don't need to keep absolute value bars anymore. All right. N plus 1 factorial squared. I want to break it down so it can cancel with this guy. So remember, it's just the same thing as having 2n plus 1 factorials. So it's n plus 1 times n factorial, each of these squared. 8n plus 1 is going to be 8 to the n times 8 to the first. And then be careful, this is 2n plus 2 plus 1, so 2n plus 3 factorial. This one's bigger than this guy, so break down the bigger one. It's going to be 2n plus 3 times 2n plus 2, keep going, times 2n plus 1 factorial. Fabulous. Then here's my 2n plus 1 factorial and 8 to the n down here. Okay. Good, good. Now, cancel party time. So oh, where did my n factorial squared go? I didn't write it down. Oh my, I got too excited about the cancel party. N factorial squared should be here. Scoot over 8 to the n. We got to make room. Okay. Now it's cancel party time. Please forgive me. N factorial squared. Be gone. 8 to the n. You too. Get out of here. Who else? 2n plus 1 factorial. Good. There's actually more, but let's not get ahead of ourselves. Okay, so we've got limit, n goes to infinity. Who survived? This 8, and then n plus 1 squared. 8, n plus 1 squared. What about downstairs? 2n plus 3, and then I could take a 2 out of there. Let me do it. 2n plus 1. That's my 2n plus 2. And then 2n plus 3. All right. Cancel. Cancel with one of these. I love it so much. Oh, and the 8 and the 2. Hello. Now that's a 4. Okay. So then we've got limit. N goes to infinity. 4n plus 4 up top. Over 2n plus 3. Divide everybody by n. Divide everybody by n. And we got limit, n goes to infinity, 4 plus 4 over n, over 2 plus 3 over n. These two guys go to 0, and I'm left with 4 over 2, which is 2. What test did I just do? This is ratio test. Ratio test, I always compare that limit to 1. 2 is greater than 1. So then that tells me the sum, n equals 1 to infinity of negative 1 to the n factorial squared times 8 to the n over 2n plus 1 factorial diverges by the ratio test. Okay, and so you don't need to check anything else. We're done. One and done. Okay, enough with conditional and absolute convergence. Now we're just going to talk about regular convergence or divergence, so you don't need to take any absolute values or whatever. But I'm not telling you what test to use, okay? So determine whether the series converges or diverges, and we have the sum n equals 1 to infinity of n to the 5th times e to the negative n. If you're like me, I don't love when there's that e to the negative n in there. Like, let's just rewrite it with a positive exponent so I can get a better feel for what's going on. So a sub n is n to the 5th over e to the n. Go through your list, right? Like first test you learned after doing telescoping series. This is not geometric. I don't want to integrate this. I don't want to make it a function and try to do integral test. And then if you do comparison or limit comparison, like what would you compare it to? Honestly, this is a nice one to just do ratio test. I know there's no factorials, but you don't have to have them. It'll work out great. Let's try it. So let's look at the limit. N goes to infinity, absolute value, n plus 1 to the 5th over e to the n plus 1, divided by a sub n, so times e to the n over n to the 5th. Okay, I don't need to keep absolute value. Everything's positive. And then we've done one very similar. Group these in the same set of parentheses. So I'm going to write it as n plus 1 over n to the 5th. And then I still have e to the n. And then down here, this is e to the n times e to the 1st. Good? And then remember, we grouped these guys together so I could write this as n over n plus 1 over n inside the parentheses. And then this is just going to be the limit now as n goes to infinity of 1 plus 1 over n to the 5th. E to the n has now canceled out of our lives forever. And we have times 1 over e. Lovely. So if n goes to infinity, 1 over n goes to 0. This is 1 plus 0 to the 5th. That's just 1. Times 1 over e, that's less than 1. Okay, and what test did I just use? Ratio test. So if the limit is less than 1, then I know my original series. I'll write it how it was. I'll write it how they gave it to me. It converges. It converges absolutely, but they didn't ask. So it converges by the ratio test. Good? I think picking the right test is the hardest thing for students, so you just have to practice. Okay, here we have the sum n equals 1 to infinity of 18 over n to the 1/4. Now, you can reference known p-series and geometric series without having to go through and prove that they converge. And this is identical to a p-series. We just have an extra 18 out front, but that's not a problem because we can write this as 18 times the sum, n equals 1 to infinity, of 1 over n to the 1/4. And we have a theorem that tells us if you take some non-zero constant and multiply by a series, if this guy converges, this won't change, and if this guy diverges, this won't change. It won't affect the convergence or divergence of the series if you multiply by a non-zero constant. So this is p-series with p equal to 1/4, which is less than 1, which tells me it diverges. So this is just a constant multiple of a divergent p-series. and we're done. So it's going to diverge also. And we didn't use a test. We just referenced p-series. If you want to do it from scratch, you would do integral tests, but why? Why when it's already been handled for you? Okay? Good. Here's another one. Why don't you stop and think what test would apply or what to do? So a sub n is 4n plus 5 over, here we go, square root 4n squared plus 5n plus 4. Now, when I'm picking what test to do, and something looks, it's not ratio test appropriate. Why do I say that? Notice this is degree 1 in the numerator. What degree is this down here? I know there's n squared, but it's underneath the radical. It's also degree 1. You guys, are the terms even going to 0? If the degree of the numerator and denominator are the same, how could this go to 0? The denominator does not have a higher degree. Let's verify. Let's consider what's the limit as n goes to infinity of 4n plus 5 over the square root of 4n squared plus 5n plus 4. Let's take that limit. I'm going to divide by n. That's the highest power from the denominator, not n squared. So this is the limit. N goes to infinity, 4 plus 5 over n. And then remember, it becomes n squared in the denominator when I put it under the radical. So this is 4 plus 5 over n plus 4 over n squared. So then 5 over n goes to 0. And so does 4 over n squared. And I'm left with just 4 over square root of 4. So this is 2. So the limit of the terms is 2, and 2 is definitely not 0, which tells me then my series, if the terms don't even go to 0, it has no chance at all at converging. So my series here diverges. What test did I use? The test for divergence, exactly. Now, you might say, well, when should I try the test for divergence? When should I think about where are the terms going? All the time. It's just most of the time it gives you no information. For example, the last problem here, the terms, where did they go? They went to 0, but that gives me no information. So I didn't even talk about it because most of the time the terms do go to 0. It goes to 0, I can't say anything. Remember, test for divergence only will tell me that my series diverges when the terms don't go to 0. If they do go to 0, I have no info and I have to pick something else. So that's why we didn't even talk about it. But when it doesn't go to 0, then it's very important that we point that out and use the test for divergence to say the series diverges. Okay? All right, let's look at another one. So we have the sum n equals 1 to infinity 6n squared plus 2 over n cubed plus 6n plus 7. Okay, so you're maybe all hyped up on that test for divergence. You're like, let's try it again. But look, this time, so we have 6n squared, that's the highest term in the numerator, and then n cubed, that's the highest term in the denominator. If the denominator is a higher degree than the numerator, then the terms are going to go to 0. Oh, so they go to 0. So what does that tell me? Nothing. Nothing, nothing, nothing. Remember, test for divergence only gives us info when the terms don't go to 0. All right, so we can't use it, so we have to pick a different test. But look, highest power was n squared, highest power was n cubed. That simplifies to 1 over n. What do I know about the sum n equals 1 to infinity of 1 over n? That's my harmonic series, and it diverges. So most likely my series diverges also. If I try to use direct comparison, remember I have to show that these terms are larger than those of the harmonic series. I don't think we can do that. So instead, let's use limit comparison test. Limit comparison test. And we do that anytime this looks kind of like a rational, I don't want to say function But yeah, I mean, it's a function whose domain is a set of natural numbers. So if you have a polynomial top and bottom, and you know it goes to 0, then try limit comparison test. But you got to choose appropriately. So let's look at the limit now as n goes to infinity. The terms of our series divided by the terms of the harmonic series, 1 over n. So now let's simplify. This is limit n goes to infinity. Let me multiply that n through the numerator. So it's going to become 6n cubed plus 2n. And then down here we still have n cubed plus 6n plus 7. And then to take the limit, let me divide by n cubed. And now we've got the limit as n goes to infinity. This is 6 plus 2 over n squared. And then 1 plus 6 over n squared plus 7 over n cubed downstairs. Okay, so 2 over n squared, 6 over n squared, 7 over n cubed. These all go to 0. So my limit just comes out to be 6 over 1, which is 6. Now, what do I care about this limit? What test did I just use? I used limit comparison test. So remember, for limit comparison, I don't care what this number is, just so long as it's finite and not 0. And then that tells me my series does the same thing as the one that I compared it to. So my series right here, the sum n equals 1 to infinity, 6n squared plus 2 over 6n cubed plus 6n plus 7. It does the same thing as the harmonic series, and the harmonic series diverges. So this guy diverges. I like to put also, right? Because that's how, when we're doing limit comparison, we compare it to somebody else. Also by limit comparison test. Perfect. Are you having fun? Okay, let's shift gears now, and we're going to look at finding radius and interval of convergence for power series. So when we're asked to find the radius of convergence, majority of the time we're going to use the ratio test. Sometimes it's better to use the root test, but if you just want to default to ratio test, you should be good. So let's go ahead and do that. I'm going to look at the limit as n approaches infinity of the absolute value of a sub n plus 1. So this time we're going to have x minus 9 to the n plus 1 over n plus 1 quantity squared times 3 to the n plus 1. And then we need to divide by a sub n. So I'm just going to already multiply by the reciprocal. You know how we do it. N squared, 3 to the n up top, over x minus 9 to the n. And this time it is important to keep the absolute value bars, because even though we know n isn't going to be negative, x could be, okay? So let's see how we can simplify. We've got the limit, n goes to infinity. I'm going to write absolute value. This time I'm going to really break it down, and then after we can skip some steps. X minus 9 to the n times x minus 9 to the first over n plus 1 quantity squared, 3 to the n times 3 to the first. And then over here, everything's already broken down all the way, and we're going to start canceling. Okay, x minus 9 to the n is gone. 3 to the n is gone. And then that's pretty much it, okay? So notice here, we're taking the limit as n goes to infinity. So here's an n, or something that involves n, and then here's something else that involves n. X minus 9 and 3, those are constants in the limit because n is changing, but x is not. So I can actually take everything that I highlighted in green out in front of the limit, just so you can focus on n, all the n's. But just keep in mind, I have to keep the absolute value bars around this quantity here when I take it outside. So watch how I'm going to rewrite it. I have absolute value x minus 9 over 3 times the limit as n goes to infinity. And then we have n squared over n plus 1 squared. Good? Okay, now you have a couple different options with taking the limit. If you want to put everything in the same set of parentheses and then divide by the highest power of n, you could do that. You could also just multiply everything out because it's not too bad, and then divide by n squared. So I'll let you choose. Let me just multiply it out. So n squared over n squared plus 2n plus 1. And then let's divide now by n squared. Everybody. And this just keep rewriting it every step of the way, okay? So then we have absolute value x minus 9 over 3. Notice there's no n's in that expression, so that's why I'm allowed to bring it out front. Limit as n goes to infinity of 1 over 1 plus 2 over n plus 1 over n squared. And then now I can take the limit, so as n gets large, both these terms go to 0. So then this entire quantity is approaching 1. So then I'm just left with the absolute value of x minus 9 over 3 times 1, so just itself. Okay, now here's the important part. We just did the ratio test. And as we've practiced extensively, after we apply the ratio test, in order for our series to be convergent, we require this limit to be strictly less than 1. And so I need to isolate this variable quantity in order to see what the radius of convergence is. So what I'm going to do is multiply 3 over to the other side. So this tells me that the absolute value of x minus 9 has to be less than 3. And that's my radius of convergence. My power series is centered at 9. Okay, so let me write you a general rule. Okay, if you have x minus a is less than r, that's your radius of convergence. And then this is where your power series is centered. It's centered at a. Sometimes you don't have this quantity here because it's centered at 0. So if you just had like absolute value of x is less than 5, then there's your radius of convergence and it's centered at 0. This one's centered at 9. So if you want now the full interval of convergence, which they did not ask for, you would keep going and solving the inequality. I'm just going to start it so you can see how it's centered at 9 and the radius is 3, okay? So we can answer the question right now. We can say, all right, the ROC is 3, radius of convergence is 3. And then if you were to take it further, rewriting this inequality without the absolute value bars is equivalent to saying -3 is less than x minus 9 is less than 3, which means if I add 9, x is between 6 and 12. So hopefully you can see why it's centered at 9. X is between 6 and 12. See how 9's right smack dab in the middle, and then there's 3 on this side, 3 on that side. That's your radius. Here's where it's centered. Go this way. Radius is 3. Okay, this just shifts it over 9 to the right if you want to think of transformations when you were graphing. Okay, I'm not going to do anything else. They only asked for the radius of convergence, so let's move on. Here we have another one. The sum n equals 1 to infinity, x minus 8 to the n over 5n factorial. So hopefully you could see this one, it's centered at 8, right? Okay, good. Let's start off, we're gonna apply the ratio test. So let's look at the limit as n approaches infinity of the absolute value of x minus 8 to the n plus 1. Please be so careful here. This is 5 quantity n plus 1, all in parentheses, and then factorial, because the 5 needs to distribute through. Divided by a sub n, so times 5n factorial over x minus 8 to the n. All right, let's get everything ready and broken down so we can have a cancel party. So x minus 8 to the n plus 1, let's write it as x minus 8 to the n times x minus 8 to the first. This factorial here, this is 5n plus 5 factorial, yes? Okay, so let's start breaking it down. I just realized I'm so slanty right now. Excuse me. Should I fix this one too? Okay. I feel better. Thanks, guys. All right. 5n plus 1 factorial is 5n plus 5 once you distribute the 5. So let's start breaking it down until I hit 5n. So it'll be 5n plus 5 times 5n plus 4 times 5n plus 3. Keep it going. 5n plus 2, 5n plus 1, 5n factorial. Whew. Times 5n factorial over x minus 8 to the n. Beautiful. So then now, who cancels? X minus 8 to the n and 5n factorial. And then again, if you want, you can take out absolute value x minus 8 in front of the limit because it doesn't involve n. So why not? So then we have absolute value x minus 8 times the limit. N approaches infinity. Let's see. There's nothing left in the numerator, so I'm just going to have 1 over everybody that didn't cancel. So all these guys here. So 5n plus 5, 5n plus 4, 5n plus 3, 5n plus 2, 5n plus 1. Nice. And then now we just take the limit as n goes to infinity. So there's no n's in the numerator. The denominator is getting very, very large. This whole quantity is going to 0. So now I just have absolute value x minus 8 times 0, which is 0. And I just applied the ratio test. So I need this limit to be less than 1. But it already is. 0 is always less than 1. So that means it doesn't matter what x is. This limit will always be smaller than 1. So if it doesn't matter what x is, then x can be any real number. If x can be any real number, then my radius is infinite. Because x can be any number from negative infinity to infinity. That's my interval of convergence, which means my radius of convergence is unbounded. It's infinite. Okay, these are some of my favorite because then it's like, boom, you're done. Fabulous. All right, next one. Now they want the full interval of convergence. So after we find the radius of convergence, we're going to have to test endpoints and do a little bit more work. So we here have the sum n equals 1 to infinity, x minus 9 to the n over 9 plus 8n. So again, ratio test time. Limit n goes to infinity, absolute value, a sub n plus 1 is going to be x minus 9 to the n plus 1 over 9 plus 8, don't forget to put n plus 1 in parentheses, divided by a sub n, so times 9 plus 8n over x minus 9 to the n. Okay, then let's break it down for cancel party time. Limit n goes to infinity, absolute value, x minus 9 to the n times x minus 9 to the first. This is going to be 8n plus 8, and then I have another 9. So this is 8n plus 17 times, let me put it in the same order, 8n plus 9 over x minus 9 to the n. Are we good? Okay, so x minus 9 to the n cancels, and then that's it, sadly. So we can take absolute value x minus 9 out of the limit because it doesn't involve n. And then just focus on the limit as n goes to infinity, and then we don't need absolute value on this portion because n isn't going to be negative, so we're good. All right, to take this limit, we can divide by the highest power of n in the denominator, which is just n to the first. So then now we have absolute value x minus 9 times the limit as n goes to infinity of 8 plus 9 over n over 8 plus 17 over n. So then these two terms here at the end, they go to 0. And then we just have 8 over 8. So we're left with absolute value x minus 9 times 1, right? Good. And remember, when we do the ratio test, we require this limit, which is just absolute value of x minus 9, to be less than 1. So already I can see my radius of convergence is 1. This is of the form x minus a, it's centered at 9, a is 9, is less than 1. So radius of convergence, we love a good abbreviation, don't we, is 1. Okay, but they wanted the full interval of convergence, so we're going to have to keep going. Now let's rewrite this inequality without the absolute value bars. So that's negative 1 is less than x minus 9 is less than 1. And then I'm going to add 9 everywhere. So then we have x is between 8 and 10. Now what I need to do is determine whether or not 8 and 10 are also part of the interval of convergence. We're not sure about the endpoints, okay? So we're going to do a test separately for each of these values, but everybody in between is good to go by the ratio test. That's the only point of ambiguity that we have. So let's start with, let's do x equals 10 first, okay? So we're testing the endpoints. And let's start with x equals 10. And so look back at your original series. I'm going to come here and substitute in 10 for x, okay? So then we have now the sum, n equals 1 to infinity of 10 minus 9 to the n over 9 plus 8n. And this is just going to give me 1 to the n, which is 1. So I don't need to write 1 to the n. I can just leave it as 1. N equals 1 to infinity, 1 over 9 plus 8n. Okay, if I look at this series, it's reminding me of just the harmonic series, right? P series, P equals 1. I suspect it's going to diverge. It's reminding me of that because I'm just looking what's the highest power of n here and here, and there's only n to the first. Now, if I wanted to show that my series diverges also, and I'm thinking, let me try direct comparison, I'd have to show that the terms of this series are larger than the terms of the harmonic series. And I can't do that, right? Because if you'll recall, here's the harmonic series, n equals 1 to infinity, 1 over n. Harmonic, and it diverges. That's just known. You can cite that. Well, the terms of my series are actually a wee bit smaller than the terms of the harmonic series, but this will diverge as well. So when you can't do direct comparison, then you're going to do very good limit comparison. Yes, so we're going to use instead the limit comparison test. And I think I told you guys before, like my students, most of the time they like this test better. They don't even want to think about direct comparison, but sometimes it's faster. So, I mean, it's good to know them all. All right, let's look at the limit as n goes to infinity of 1 over 9 plus 8n over 1 over n. So this is going to be the limit as n goes to infinity. That 1 over n will flip up to the numerator, so then you just have n over 9 plus 8n. And then divide by n, and we have now the limit as n approaches infinity of 1 over 9 over n plus 8. So then 9 over n goes to 0, and this limit ends up being 1/8. Okay, be careful. We just used the limit comparison test. So what am I interested in? I just want to make sure this limit is finite and not 0. And then the limit comparison test tells me that my series behaves the same or is twinsies with, yes, this divergent harmonic series. So this guy also diverges by the limit comparison test, which tells me that x equals 10 does not belong to or is not an element of the interval of convergence, okay? So when I substituted x equals 10 into my series, it diverged. So then it's not going to be inclusive here. I know for sure x has to be strictly less than 10. It can't equal 10. But I have one more endpoint to check, and that is x equals 8, right? So now let's test that endpoint. I'm going to substitute in 8 there for x. So x equals 8. And there is no like guaranteed way of saying, oh, because, 10 wasn't part of it, 8 won't be a part of it. No. Sometimes one works, the other doesn't. Sometimes both work, sometimes both are not. So you have to always test both. All right, good. Glad we got that out of the way. So we have the sum, n equals 1 to infinity, 8 minus n to the n over 9 plus 8n. Now this time 8 minus 9, that's negative 1. So I have to keep it there. And notice we actually have an alternating series. So yes, we need to use the alternating series test. So let's first identify b sub n. B sub n is everything without the negative 1 to the n part. So 1 over 9 plus 8n. And then we have to check the two conditions of the AST. So first I want to see, is b sub n decreasing? I can just use the definition. So b sub n plus 1 is going to be 1 over 9 plus 8 times n plus 1. And I mean, I can already tell, right? For sure, I just made the denominator larger than what b sub n has. So this is going to be smaller than 1 over 9 plus 8n, which is b sub n. So yep, the terms are decreasing. And then the second thing I need to check is what's the limit as n goes to infinity of 1 over 9 plus 8n. Well, this is going to infinity, so the whole thing's going to 0. Perfect. That's the other condition I required. So then I know the sum, n equals 1 to infinity, negative 1 to the n, over 9 plus 8n. It converges by the alternating series test. So that tells me x equals 8 is part of the interval of convergence. Okay, so then if 8 is included but 10 is not, you could write your interval of convergence a couple of different ways. If you want to use interval notation, you would have bracket on 8 and then parentheses on 10. Or you could say 8 is less than or equal to x is strictly less than 10. Okay, I would use interval notation because it's an interval of convergence, but same thing. Okay, how was that one? Let's try another. All right, here's a lovely one. We have the sum n equals 1 to infinity, x minus 6 to the n over 2n factorial. So start off, let's do the ratio test. I'm going to take the limit, n goes to infinity, absolute value. This is going to be x minus 6 to the n plus 1 over 2 times n plus 1 factorial times reciprocal of an, so 2n factorial over x minus 6 to the n. Good. So then breaking everything down, limit n goes to infinity, absolute value, x minus 6 to the n times x minus 6 to the first. And then this is 2n plus 2 factorial. Yes? So then if I break it down until it cancels with 2n factorial, we're going to have 2n plus 2 times 2n plus 1 times 2n factorial. And then here's 2n factorial, x minus 6 to the n over here. All right, fabulous. Now cancel party time. So x minus 6 to the n is gone, and then 2n factorial is also gone, and that's about it. So if you want, now we can take absolute value x minus 6 out of the limit, and then we just have limit, n goes to infinity. There's only a 1 left in the numerator now, and then we have 2n plus 2 times 2n plus 1. Beautiful. Well, as n goes to infinity, this quantity goes to 0. And then I'm just left with absolute value of x minus 6 times 0. We've had this happen to us before. This is just 0, which is always less than 1. So that means my series will converge for all x's. Therefore, I already have my interval of convergence. It's from negative infinity to infinity. They didn't ask for the radius of convergence, but let's just give it to them. It's infinite. And these are literally my favorite because you don't have to test endpoints. You don't have to do anything. It's like, ooh, surprise bonus, very little work to get the answer. And that's it. Beautiful. Beautiful. Okay, let's look at another. I told you majority of the time you do the ratio test. On occasion, it's nicer to do the root test, and this is an example of one. Now, if you didn't notice and you did the ratio test, you'd be perfectly fine. It would still work out. So if you just want to say, Professor V, I don't like that root test as much. I don't want to mess with it for interval and radius of convergence. I feel you. I like the ratio test way better. But let's do the root test just so we practice it a little bit, okay? You don't have to, though. If you want to do this one differently as I'm working through, you live your best life. So we've got limit, n goes to infinity. We're going to take the nth root of the absolute value of a sub n. So x minus 4 to the 2n over 4 to the n. And then remember, when we take the nth root, we divide each of the exponents by n because you're raising them to the 1 over n. So it's going to end up dividing. So we've got limit, n goes to infinity, absolute value, x minus 4. If I divide 2n by n, it's just 2. And then this becomes 4. There's no n's, right? There's no n's. So the limit's done. I just have absolute value, x minus 4 squared over 4. Oh, how peculiar. Let's split the absolute value up, actually. I want to write it like this. X minus 4 squared over 4, right? Because the denominator's already, it's just a constant. And we did the root test. I need this limit to be less than 1. So let me multiply the 4 over. So we have x minus 4 squared is less than 4. But remember, when you're finding your radius of convergence, it has to be in the form x minus a is less than r. It's not yet because there's this squared here. So let me take the square root of both sides. Then this means absolute value of x minus 4 is less than 2. Boom. There's my radius of convergence. And then this guy is centered at 4. Okay, so let's rewrite this inequality without the absolute value bars. We have x minus 4 is less than 2 and greater than negative 2. And then if I add 4, I get x is between 6 and 2. So now I need to see whether or not I'm going to include the endpoints of 2 and 6. So let's go ahead and test them, okay? How are you guys doing? Okay, let's test our endpoints. Starting with, let's do x equals 6. So go back to the original series and you're going to substitute in 6 for x right here. So we've got the sum, n equals 0 to infinity, 6 minus 4 to the 2n over 2 to the 2n. Oh, hold on, I got too excited. It was temporarily 4 to the n. Let me stay there and relax a little bit. Okay, and then if I rewrite this, this is the sum, n equals 0 to infinity. 6 minus 4, that's 2 to the 2n. And then I wanted to show you guys 4 to the n is also 2 to the 2n. Because 4 to the n is 2 squared to the n, so you could write that as 2 to the 2n. And then this is just the sum, n equals 0 to infinity of 1, right? 2 to the 2n over 2 to the 2n cancels. And I can tell right away, I'm just adding up a bunch of 1s. Of course, this is going to diverge. What test am I applying? Basically, test for divergence, right? The limit as n goes to infinity of a sub n of the terms of my series is just a constant. It's just 1, which isn't 0. So then that tells me this series diverges by the test for divergence. And then therefore, what can I conclude about x equals 6? That it's not part of the interval of convergence. Okay, now let's see what's going on with the other endpoint. Now the other endpoint is at x equals 2. So let's substitute that into the series. We have 2 minus 4 to the 2n over 4 to the n. And if we simplify a bit, this is the sum, n equals 0 to infinity. 2 minus 4, that's negative 2 to the 2n over 4 to the n. And I want you to notice something. Negative 2 to the 2n, that's the same as negative 2 squared raised to the n. So that's 4 to the n. So then now we have same scenario as we just did a second ago. This is 4 to the n over 4 to the n. So this is the sum, n equals 0 to infinity of 1. 1 to the n, or 1. So again, same thing, it diverges by test for divergence. You alternatively could say this is geometric also. Absolute value of r equals 1, which means it diverges. Because remember, geometric series r has to be, absolute value of r has to be strictly less than 1. So two ways, test for divergence, or you could say, hey, it's a geometric series, it's going to diverge. Either way, that tells me that x equals 2 is not a part of the interval of convergence. So then the interval is from 2 to 6, not including either endpoint. All right, good. Let's move on. Some more stuff with power series. Find the sum of the series as a function of x. So we actually did problems just like this earlier in the unit looking at geometric series, and we're in the same scenario now. It's just we have an expanded knowledge of power series. So we're being asked the same question. So find the sum of the series as a function of x. You need to first identify the fact that this is essentially a geometric series, and absolute value of r would be absolute value of x plus 5 over 7. And we know our geometric series converge when this r is strictly less than 1. That means the series converges. So if I'm going to find the sum, it's going to be the first term over 1 minus r. And what's the first term of this series? Well, it starts at n equals 0. So if I have all of this stuff raised to the 0, the first term's just 1 over 1 minus the radius here, x plus 5 over 7. And then certainly we would not leave our final answer like that. Multiply everybody by 7, so we clear up that complex fraction. So now we've got 7 over 7 minus x plus 5. And then if you simplify in the denominator, we have 7 over 2 minus x. Beautiful. That one's pretty straightforward, hopefully. Same thing here. Find the sum of the series as a function of x. So the radius is x squared plus 4 over 3. And we require absolute value of the radius, so absolute value of x squared plus 4 over 3 to be strictly less than 1. And the first term of the series, again, it starts at 0, 0 to, so all of that raised to the 0 is just going to be 1. So the sum is 1 over 1 minus x squared plus 4 over 3, multiply by 3. And then this is going to be 3 over 3 minus x squared plus 4. And then clean up in the denominator. This is 3 over 3 minus x squared minus 4. So that's going to be negative x squared minus 1. I don't love how that looks. Look, we could take the negative out, and then it's x squared plus 1. And then you never leave that negative in the denominator. I'm going to write it as negative 3 over x squared plus 1. That's like a million times cuter looking, you know? Good. Fun, fun. Now for the exciting part. If nothing excited you thus far, hopefully this does. Find the Taylor polynomial of order 3 generated by f at a. So since our Taylor polynomial is only order 3, we're going to find t sub 3 of x. And that's the sum, n equals 0, and we're going to stop at 3 of the nth derivative at a times x minus a to the n over n factorial. When you find a full Taylor series, then you take this as an infinite sum, but we're stopping at n equals 3 here for this particular one. Okay, notice they told me a is 1, so I'm going to substitute in 1 there, and then now I need to find all these derivatives. Don't freak out when you do Taylor series. If you haven't watched my video on it, I break it down so beautifully, but there's always 3 parts to each term. 1, 2, 3. Okay, so we're going to make a table to find that first part. So n, then we need the nth derivative at x, and then once I have all those, I'm going to evaluate it at 1. Okay, and we're only going up to n equals 3, but we do start at 0. Now, if I could only draw a straight line to save my life, there we go. N is 0, 1, 2, 3. So the 0th derivative is just the original function. I'm going to write it as x plus 10 to the negative first, since I want to get ready to take a bunch of derivatives now, okay? Taking one derivative, it's going to be negative x plus 10 to the negative second. Take another one, 2 times x plus 10 to the negative third. And then one more, negative 6 times x plus 10 to the negative fourth. And then now we substitute in 1 for x. So that's going to be 11 to the negative first, or 1 over 11. Next one's going to be negative 11 to the negative second. So negative 1 over 11 squared, which is 121. This is 2 over 11 cubed, which is 2 over 1331. And then negative 6 over 11 to the fourth, which is 14641. Yeah, Pascal's triangle. Cool, huh? So then now we're ready to put everything together, okay? So t sub 3 of x is equal to, this table gives me all of the blue parts, one part of each of the terms. So we're going to have 1 over 11, x minus a, which is 1 to the 0 over 0 factorial. This is for n equals 0. Here's this part, x minus a to the n factorial. Next term, negative 1 over 121. So I have minus 1 over 121, x minus a, which is 1 to the first over 1 factorial. So here, here, here. Good? Next term, plus 2 over 1331, x minus a squared over 2 factorial, 1, 2, 3. Just keep counting to 3. Make sure you got everybody. Minus 6 over 14641, x minus 1 cubed over 3 factorial. 1, 2, 3. And then just simplify for your final answer. So then we're going to have, let's see, t sub 3 of x. Now, this is just 1. 0 factorial is 1. So this is just 1 over 11 minus x minus 1 times 1 over 121. We don't need to put the 1 factorial. Leave it like that. Plus, now 2 factorial is 2. It's going to cancel with this 2 up here. So then I have 1 over 1331 times x minus 1 squared. And then same thing, 3 factorial is 6. So those cancel. Minus 1 over 14641 times x minus 1 cubed. And that's it. Beautiful. See how fun? Once you get the pattern down and you just tell yourself this isn't bad. If you tell yourself, oh my God, it's so scary, Taylor series are so hard, you're going to freak out. You're going to have a meltdown. But don't talk like that to yourself, okay? You can do this. You got this. All right, let's do another one. Why don't you pause the video, try it on your own? I'm serious. I think you can do it. F of x is e to the negative 6x. A is 0. So technically it's a Maclaurin series, right? Because a is 0. But, you know, we can still call it Taylor series. Okay, here we go. Still order 3. Did you try it? I hope so. Nth derivative at 0. So always start with the table. Get it together. Okay. 0, 1, 2, 3. So the 0th derivative is the original function. Then we take one derivative, multiplying by -6 because of the chain rule. Another derivative, I'll multiply by another -6. And then lastly, -216 e to the -6x. And then all of these get evaluated at 0. So e to the 0 is 1. This will be -6, 36, -216. Okay, so t sub 3 of x is going to be 1 times x minus 0 to the 0 over 0 factorial. Remember, these are the blue parts here, and then that's part 2, and that's part 3. I'm not going to keep writing x minus 0. It's just x, okay? Next, I'm going to have -6 times x to the first over 1 factorial plus 36x squared over 2 factorial minus 216x cubed over 3 factorial. So here's all of the constants that we got from the table, x to the n, and then these are the n factorials. And then now we just simplify. So t sub 3 of x, this is just 1 minus 6x plus, this is going to simplify to 18x squared minus, remember 3 factorial is 6, so 216 divided by 6 is 36. Ooh. Okay, how was that one? Are you less intimidated now? Oh, good. That was exactly what I wanted to hear. You're like, I knocked it out of the park, Professor V. Brilliant. Okay, I got another one, and then we'll move on to Maclaurin series. F of x is ln of x, and a is equal to 10. So again, we're just doing order 3, so up to n equals 3. So nth derivative at x, and then nth derivative at 10 in this case. 0, 1, 2, 3. So nth derivative, so 0th derivative is just the original function, ln of x. First derivative would be 1 over x. Second derivative, -1 over x squared. And then third derivative, 2 over x cubed. And then let me substitute in 10 now. So this would be ln of 10, 1/10, -1 over 100, and 2 over 1,000. All right. Let's put it all together. So t sub 3 of x is going to be ln of 10 times x minus 10 to the 0 over 0 factorial plus 1/10 times x minus 10 to the first over 1 factorial minus 1 over 100 times x minus 10 squared over 2 factorial plus 2 over 1,000 times x minus 10 cubed over 3 factorial. Okay, so let's clean up. T sub 3 of x. That's 1. So then we just have ln of 10 plus the next term's just going to be 1/10 x minus 10 minus, now 2 factorial, that's just 2 times 100. So let me write 1 over 200 x minus 10 squared plus, and then 3 factorial is 3 times 2 times 1. So this 2 cancels, and then I have 1,000 times 3 in the denominator. So that's going to be 1 over 3,000 times x minus 10 cubed. And that one's done. Super straightforward. Like if you remember the formula and you can take derivatives, you can do this. You can do this. Okay, now we're finding the full series, like the infinite sum. And we're going to use the definition. So find the Maclaurin series for the given function using the definition. So here we go. So let's remind ourselves, definition for Maclaurin series, f of x is the sum n equals 0 to infinity of the nth derivative at 0 times x minus 0 to the n over n factorial. So it's Taylor's series, but centered at 0. That's why you have x minus 0 to the n. Okay, so we're going to, again, just start off making a table. It's just this time, there's no set n to cut it off at. So you just do however many you need until you can see a pattern, because we're going to have to come up with a rule for how to write this out for the general term. So honestly, like usually 3 does it for me. Oh, and we already did e to the negative 6x just a hot second ago. Sorry guys, I'm writing so slanty. Let me straighten it up. Okay. Now this one's gonna bug me. You know what I mean? It's like, all right. 0, 1, 2, 3. I think that's gonna be enough. E to the negative 6x, negative 6 e to the negative 6x, 36 e to the negative 6x, and then negative 216 e to the negative 6x. Now, sometimes when I'm trying to write out like the full series and I'm looking for a general rule or pattern, I actually don't write these as 36 or 216. What I mean is sometimes I'll write it as 6 squared or 6 cubed to kind of help me see the pattern that's emerging. So watch, I'm gonna do that here. So this will be 1 if I substitute in 0 for x. This will be negative 6. This is going to be positive 6 squared, negative 6 cubed, like that. It's going to help me out a little bit. So then let's start listing out the first few terms. We're going to have 1 times x minus 0 to the 0 over 0 factorial minus 6x to the first over 1 factorial plus 6 squared x squared over 2 factorial minus 6 cubed x cubed over 3 factorial. And then I didn't even do the fourth one, but I can tell it's going to be plus 6 to the fourth x to the fourth over 4 factorial, right? So on and so forth. So can you come up with a pattern or a rule? Remember, this is helpful. There's 3 parts to each term. So here's part 1. And then here's part 2, here's part 3, and then part 4 PS, it's alternating. We'll take care of that last. That's no big deal. Okay, so this is the sum, n equals 0 to infinity, part 1. 1, 6, 6 squared, 6 cubed, 6 to the fourth. This is 6 to the 0, 6 to the first, 6 squared. This is the n equals 0 term. This is the n equals 1 term. This is the n equals 2 term. So whatever n is, you have 6 to the n in the numerator. Okay. Part 2, x to the 0, x to the first, x squared. We also have x to the n. Part 3, 0 factorial, 1 factorial, 2 factorial, 3 factorial. We have n factorial in the denominator. And then the last thing is it's alternating. So that means you're going to have either negative 1 to the n or negative 1 to the n plus 1, which is the same as negative 1 to the n minus 1. You just got to see, are the odd terms positive or are the odd terms negative? So this is n equals 0. Negative 1 to the 0 would be positive 1, and the first term's positive. That looks good. So I'm guessing it's going to be just negative 1 to the n. Let me confirm. Now, if n is 1, negative 1 to the first is negative. Yep, this guy's negative. N equals 2, negative 1 squared is positive. Yep, that one's positive. So this is it. But it looks ugly. So I'm going to write f of x is the sum, n equals 0 to infinity, negative 1 to the n, 6 to the n, x to the n, over n factorial. And that's it. Beautiful. Okay, that wasn't bad. You just have to find the pattern at the end, you know? Okay, let's look at another one. 1 over 3 plus x. So make the table until you see a pattern or you feel comfortable. These are all Maclaurin series, so A is 0. I'm going to just go up to 3. Usually that's enough for me. I'll show you one where we need a little bit more than 3 after this. 0, 1, 2, 3. So the 0th derivative, I'm going to write it as 3 plus x to the negative first. Then take one derivative, it's negative 3 plus x to the negative second. Another derivative, this is 2 times 3 plus x to the negative third. One more, negative 6, 3 plus x to the negative fourth. Okay? Good, good, good. And then evaluating these at 0. So this is going to be 3 to the negative first, which is 1/3. This is going to be negative 1 over, let me just leave it 3 squared. The next term is going to be 2 over, again, I'm leaving it 3 cubed, just to help me see the pattern better. And then this is negative 6 over 3 to the fourth. Honestly, leave it, okay? So then we have f of x equals 1/3 x to the 0 over 0 factorial minus 1 over 3 squared. Let me just write it normal like that. And then we have x to the first over 1 factorial plus 2 over 3 cubed times, I had to stop and think for a second, did I mess up? No, I did not. X squared over 2 factorial minus 6 over 3 to the fourth times x cubed over 3 factorial plus blah, blah, blah. Let's clean up, okay? I'm gonna write this 1/3 out front because I'm not liking how it looks, okay? So I'm gonna have x to the 0 over 3 times, I'm leaving the 0 factorial. I'm not going to write 1 because I just want to see the pattern. I got to come up with the rule for this series this time, so I want to see the pattern. I'm not going to simplify too much. Minus, this is 1 over 3 squared times x to the first over 1 factorial. Plus, notice here, this 2 cancels with the 2 factorial. So then I just have x squared over 3 cubed minus, oh my god, it's happening again, 6, that's 6. So then this is x cubed over 3 to the fourth plus blah, blah, blah. So then now I'm noticing, oh, the factorials all cancel. So I don't really need to stress out about them here because these are just ones anyways. Okay, so then now my paranoia can subside somewhat. Let me just write this as x to the 0 over 3 to the first minus x to the first over 3 squared plus x squared over 3 cubed minus x cubed over 3 to the fourth plus blah, blah, blah. Okay, now I feel good. So this is the sum. N equals 0 to infinity. Let's start with the most obvious part. We have x to the n in the numerator over 3. Notice on n equals 0, 3 is raised to the first. On n equals 1, 3 is squared. So 3 is raised to the n plus 1. And then PS, it's alternating. It is alternating. The first term is positive. So then we're going to have negative 1 to the n. And that's it. Yep. So it's kind of a little game. Like sometimes you don't know, should I simplify and replace these with ones right off the bat or not? Because look at last time I left them. See how I left them and it was very helpful. But in this case, all the factorials ended up canceling here. So then I realized, oh, I don't need to worry about keeping them to see the pattern. You just got to play around with it. Now's your turn. I want you guys to try this one, okay? And with sine and cosine, I usually do more than n equals 3 because you'll notice every other derivative often ends up being 0. So you lose information, like you lose terms as you go. So you got to do a little bit more than 3. You'll see what I mean right now. Why don't you pause the video and take about, I'm going to tell you right now, take 5 derivatives, okay? Did you do it? I'm going to go quickly, okay? So I hope you did it. 1, 2, 3, 4, 5. Okay. So original function, sine 9x. One derivative, 9 cosine 9x. Another one, I'm going to write negative 9 squared sine of 9x. Then negative 9 cubed cosine 9x. 9 to the 4th sine of 9x. Then 9 to the 5th cosine 9x. Now we evaluate these at 0. So this is going to be 0, 9, 0, negative 9 cubed, 0, 9 to the 5th, etc. So you see how every other term is just going to be a 0. So we don't have as many terms as we do normally when we make the table. It's okay though. We can see the pattern. So let's start writing out f of x equals, well, this one's 0. So now this is for n equals 1. I have 9 times x to the 1st over 1 factorial. Then skipping this guy, now for n equals 3, I have minus 9 cubed. If n is 3, it's going to be x cubed over 3 factorial. And then nothing here. Now this is for n equals 5. So plus 9 to the 5th, it would be x to the 5th over 5 factorial. And I didn't keep the table going, but hopefully you can see the pattern, right? It's going to be minus 9 to the 7th, x to the 7th over 7 factorial, etc. Okay, so we have to come up with a way to write this in sigma notation. And I know originally this was n equals 1, n equals 3, n equals 5, but now we have to write this as its own series all by itself, not based on the Maclaurin formula. So this is my new n equals 0, n equals 1, n equals 2, n equals 3. Don't worry about like these n's here when we're writing the rule for our Maclaurin series. So starting with n equals 0 to infinity, notice 9 is always raised to an odd power. X is always raised to an odd power, and the factorials are all odd. To represent an odd integer, you use 2n plus 1 or 2n minus 1. An even integer is 2n. Like whatever you plug in for n, if you double it, it's even. And then if you add or subtract 1 from an even number, it's now odd. So if I'm starting at n equals 0, then I'm going to represent all of the odd powers as 2n plus 1. Because you're going to have 9 to the 2n plus 1. X is also raised to the same power. And I have the same factorial in the denominator. See? And if n is 0, 0 plus 1, 9 to the 1st, x to the 1st, 1 factorial. If n is 1, this is 9 cubed, x cubed, 3 factorial. N is 2, 9 to the 5th, x to the 5th, 5 factorial. So just put this to memory here. One more thing I need to do, I need to make it alternate, and the first term is positive, so we're just going to have negative 1 to the n, and we're done. Bada bing, bada boom. Nice, right? Okay. Now, some Maclaurin series are worth memorizing. So I showed you in the video lecture the ones that I would put to memory. Let me remind you of them right now. Here are important Maclaurin series and radii of convergence, because sometimes you're allowed to reference a known Maclaurin series, and these are the ones. First and foremost, you have to have this bad boy memorized because we're going to use it to find power series representations of functions in a hot second. And then e to the x, sine x, cosine x, for sure memorize those. Tan inverse of x, it's up to you. I'll show you how to derive it. It's not too bad. But if you want to memorize it, go for it. And then ln of 1 plus x, again, up to you. Ask your instructor. But for sure, memorize these first 5. And then to me, sine and cosine is pretty easy to remember. Sine of x is an odd function. You should remember that hopefully from trig and pre-calc. And notice it's all odd powers of x and odd factorials like we just saw. And cosine is an even function, and it's all even powers of x with corresponding even factorials in the denominator. So I'm going to be referencing these now to do the following examples because the directions tell us that we can use known Maclaurin series. So we don't need to work with the definition and start from scratch. We can manipulate one of these guys. So the directions say find the Maclaurin series for the given function using known Maclaurin series, and we have f of x equals x to the 8th times sine of x. So looking through, I go, okay, well, what's a Maclaurin series that I know that's involved here that I could use as my starting off point? And it's sine of x. So in case you don't have it memorized, let me rewrite it. Sine of x is the sum, n equals 0 to infinity, of negative 1 to the n times x to the 2n plus 1 over 2n plus 1 factorial. Now, let me manipulate this until it matches f of x. And there's only really one thing I need to do, namely multiply by x to the 8th on both sides. X to the 8th here and x to the 8th here. So then I'm just going to simplify, and I can add my exponents there together. And then now I have f of x is the sum, n equals 0 to infinity, negative 1 to the n, x to the 2n plus 9 over 2n plus 1 factorial, and we are done. Yep, that easy. When they tell us we can use a known Maclaurin series, okay? And we don't have to work with the definition. Let's try another. That was just way too easy. Find the Maclaurin series for the given function using known Maclaurin series. Again, this starting off point is going to involve sine of x. So let me remind you, sine of x is the sum, n equals 0 to infinity, negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. So what's different? Notice we have sine of 3x in the function, not sine of x. So I'm going to come in and replace x with 3x in the sum. So we have n equals 0 to infinity, negative 1 to the n, 3x to the 2n plus 1 over 2n plus 1 factorial. And then if you want, or even if you don't want, you should distribute this exponent through. So we have negative 1 to the n, 3 to the 2n plus 1, x to the 2n plus 1 over 2n plus 1 factorial. Good? Okay, now let's see, are we there yet? Do we have f of x? Well, right now I just have sine 3x, sine of 3x over here. To make it match the function given, I need to divide by x. I need to multiply by 1 over x. And always, from here, simplify as much as possible. 2n plus 1 and x, I can simplify because this is x to the first, right? And then this is just going to become x to the 2n in our final answer. So then we have sine of 3x over x equals the sum, n equals 0 to infinity, negative 1 to the n, 3 to the 2n plus 1, x to the 2n over 2n plus 1 factorial. And we're done. How was that? Fun, right? I like these ones because they're not too stressful. They're not stressful at all. Okay. Find the Taylor series generated by f at x equals a. So earlier we found Taylor polynomial of degree 3, so we just cut it off there. Then we found Maclaurin series where we wrote out the full sigma notation. Now we're going to find Taylor series. We're going to have to write out the full sigma notation. We're not cutting it off at any particular n. So again, we're going to have to find the pattern and whatnot so that we can express a rule to find the general term. So here we go. It's table time. Oh yeah. How many are you going to need? I'm going to do 4. You could do 3 maybe if you're feeling confident. I think you guys are. Nth derivative at x and then nth derivative at a, which is 10. straighten up now. Okay, so we're going to go 0, 1, 2, 3. I'll go to 4 today. 2, 3, 4. So 0th derivative is the original function. Let me write it, x to the negative second. First derivative is going to be negative 2, x to the negative third. Another one, 6x to the negative fourth. Negative 24, x to the negative fifth. 120, x to the negative sixth, and then so on and so forth. And then evaluating these at 10. So this is going to be 10 to the negative second. Negative 2 times 10 to the negative third. 6 times 10 to the negative fourth. Negative 24 times 10 to the negative fifth. 120. See how I'm leaving it 10 to the whatever? Because I want to see the pattern. Okay, so let's start listing out all of the terms here for our Taylor series. So remember, this is one of 3 parts from the table. So 10 to the negative second, then we have x minus a, which is 10 to the 0 over 0 factorial. Next term, minus 2 times 10 to the negative third, x minus 10 to the first over 1 factorial, plus 6 times 10 to the negative fourth, x minus 10 squared over 2 factorial. Next is minus 24 times 10 to the negative fifth, x minus 10 cubed, because that comes from n equals 3 over 3 factorial, plus, okay, I'm out of space. That's enough. Let's clean up a little bit because I want you to notice something. This is 10 to the negative second times x minus 10 to the 0. 0 factorial is just 1. Minus 2 times 10 to the negative third times x minus 10 to the first. Plus 2 factorial cancels with 6, and this is just a 3 now. So 3 times 10 to the negative fourth times x minus 10 squared. Minus 3 factorial is 6, so this is just going to be a 4 now. 4 times 10 to the negative fifth times x minus 10 cubed, plus so on and so forth. So look what's going on here. We've got, x minus 10 to the n. That part's fine. Then we've got 10 raised to negative n plus 2, right? Because this is n equals 0, it's to the negative second. This is n equals 1, negative 3. N equals 2, negative 4. And then last little piece, we've got here n plus 1 in the front. And maybe you can't see it, but you know, there's a 1 being multiplied there. And it's alternating. Okay, so here we go. Don't have a meltdown. You got this. Starting n equals 0 to infinity. Part 1. 1, 2, 3, 4. The next one would have 5. This is the n equals 0 term. So that's n plus 1. First term, it's a 2. N plus 1. N plus 1, n plus 1. So we've got n plus 1. Then we've got 10 to the negative n plus 2. Then we've got x minus 10 to the n. And no more factorials, but this guy is alternating. First term is positive, then negative. Positive, negative. So we're going to have negative 1 to the n. Now that looks disgusting. Don't leave negative 1 to the n on the end like that. And then I can bring this guy, put it in the denominator, and make the exponent positive. So then this is the sum. N equals 0 to infinity. Let me put that negative 1 to the n first. Then n plus 1. Then x minus 10 to the n over 10 to the n plus 2. Good? Okay, I think that's the messiest one we've done. If you saw the pattern and you could do that one, you are in business. I got one more Taylor series for you guys. This one's going to be a little bit nicer, actually. So again, find the Taylor series generated by f at x equals a. So full sigma notation, find the pattern and everything. So n nth derivative at x, and then nth derivative at a, which is 3. E to the 8x, hopefully you're like, ooh, that's going to be so relaxing to differentiate. It will. I think we can just go up to 3 and we'll be golden. So this is e to the 8x, 1 derivative, 8e to the 8x, 8 squared e to the 8x, 8 cubed e to the 8x. And then now substituting in 3 for x, this is e to the 24, 8e to the 24, 8 squared e to the 24, 8 cubed e to the 24. We got it. Okay, so f of x is going to be e to the 24, x minus 3 to the 0 over 0 factorial, plus 8e to the 24, x minus 3 to the first over 1 factorial, plus 8 squared e to the 24, x minus 3 squared over 2 factorial, plus 8 cubed e to the 24, x minus 3 cubed over 3 factorial, etc. Okay, I feel ready. Do you feel ready to write the pattern? And look, this guy's not alternating. Everybody's positive. So there's e to the 24 in every single term, and it doesn't change. It's just a constant. So, okay, that's going to go there. Then notice we have technically 8 to the 0, right? 8 to the 0, 8 to the first. 8 squared, 8 cubed. So we've got 8 to the n. Then we have x minus 3 to the n. Do you see that part? X minus 3 to the n. And then we have good old n factorial in the denominator. That's the last piece of the puzzle. Yep, and we're done. That one was easy peasy, huh? After the last example. Good. Hopefully you could get this one on your own. For sure. Okay, last chunk of problems has to do with power series. If you haven't watched my video, Power Series Made Easy, you really need to, because I break down finding the power series representation of a function into 3 possible cases. And if you identify them, it makes this whole process really easy peasy. And I'm going to refer to the solution techniques that I used in that video. So watch it so you have context. Okay, we need a power series representation for x cubed over 1 minus 2x. This one I can come up with just by manipulating algebraically 1 over 1 minus x. So remember, 1 over 1 minus x, the power series representation for that function is the sum n equals 0 to infinity of x to the n. Right off the bat, I see I have a 2x instead of an x, so I'm going to go ahead and replace that. So power series representation for 1 over 1 minus 2x is the sum n equals 0 to infinity of 2x to the n. So literally just come replace x with 2x. Now, you don't ever leave it like that. You want to get x to the something all by itself. So you're going to distribute that exponent, write this as the sum, n equals 0 to infinity, 2 to the n, x to the n, like that. And then now we're almost done. The only thing that's missing is this function has an x cubed up top. So I'm going to multiply by x cubed up top, multiply by x cubed here. So then now I can say x cubed over 1 minus 2x is the sum, n equals 0 to infinity, 2 to the n, x to the n plus 3. Boom, done. Yeah, it really is that easy. I think people get in their head about these power series. They're really fun. X to the 6th over 1 plus 8x. So start off, like, don't look at the numerator. Just go, ugh. I wish you weren't there, x to the 6th, so I'm going to make it happen. And then you always want 1 minus something in the denominator. So 1 minus negative 8x. I can write this as the sum, n equals 0 to infinity, negative 8x to the n. You guys, I'm minimally explaining because I'm assuming you watched the other video. Okay. Then I can rewrite this. This is the sum, n equals 0 to infinity. When you have a negative, you always want to break it off separately. So that's negative 1 to the n, 8 to the n, x to the n. Perfect. Now, was this exactly the function I was given? No, it's missing x to the 6th. So let's multiply by x to the 6th on both sides, and then we're done. So x to the 6th over 1 plus 8x is the sum n equals 0 to infinity, negative 1 to the n, 8 to the n, and then you just write x to the n plus 6. Good? Okay. Now let's take the spice level up a notch. F of x is 1 over 1 minus 6x squared. Now you might say, oh, okay, I know how to find a power series for 1 over 1 minus 6x. Let me just get that and then square it. No, so sorry. Often in my math career, I wanted to square a series, but that's never the answer. At least not at this level in your Calc 2 class. Don't square an infinite sum, okay? So what do we do instead? Well, we are going to first find the power series representation for 1 over 1 minus 6x. We sure are. That's the sum n equals 0 to infinity, 6x to the n, which I can write as the sum n equals 0 to infinity, 6 to the n, x to the n. Now, anytime you want the denominator to go up a degree, you're going to actually differentiate this function and differentiate the corresponding power series representation for it. So I want to remind you, this is 1 minus 6x to the negative first. So I'm going to differentiate both sides with respect to x, okay? So we're going to take the derivative with respect to x of the sum n equals 0 to infinity, 6 to the n, x to the n. Okay, derivative over here is going to be negative 1 times 1 minus 6x to the negative second. And then don't forget the chain rule. We have to multiply by the derivative of 1 minus 6x, which is negative 6. And then now I'm going to differentiate my power series. So anytime you take the derivative of a power series, be careful because we're starting at n equals 0. So the first term would be 6 to the 0, x to the 0, which is 1. Then the next term is 6 to the first, x to the first. Then the next term is 6 squared, x squared, and so on and so forth. But when I take the derivative with respect to x of this power series, the derivative of that first term, since it's a constant, is 0. So now my series is going to start at 1. So don't forget, you always start the index 1 higher when you differentiate your power series because you lose that constant term, that first term. And then here, don't freak out. Please don't freak out. You got this. This is a constant, so you just leave it alone. And then the derivative of x to the n would be n times x to the n minus 1. Yes. So when you differentiate constant times a function, the constant just comes along for the ride. Don't touch. Derivative of x to the n, we bring the exponent down front, subtract 1, and then the only little spicy part is make sure you bump up the index by 1 because we lose the 0 term. Okay, we're almost done. Now we just clean up this guy. So on the left-hand side, we have negative 1 times negative 6. So it's positive 6 over 1 minus 6x squared. And then this is the sum. N equals 1 to infinity, 6 to the n times x to the n minus 1. And then you just check, is this on the left-hand side my f of x? Almost. I have a 6, but I want a 1. So let me multiply by 1/6. Let me multiply by 1/6, and then I'm there, right? Now this is f of x, which is the sum, n equals 1 to infinity. This is 6 to the n times 1 over 6, which is 6 to the negative first. So I could write that as 6 to the n minus 1 times n times x to the n minus 1. And as relieved as you may be at this point, we don't stop here because whenever possible, we want to write our final answer with just x to the n, not x to the n minus 1. So I'm going to shift the index. I want this to go up by 1. So then all of these n's are going to go up by 1. So this will be n plus 1. This will be n. And then to preserve what this sum represents, I have to start 1 lower at n equals 0. Okay, if you need help shifting indices, then go watch some of the videos where I review sigma notation. So n equals 0 to infinity. Then I can write this as 6 to the n. This is n plus 1. This is x to the n. Because look, if n is 1, this is x to the 1 minus 1, which is 0. But if all of a sudden I make it n, for the first term to be x to the 0, I got to start one lower. So they always move in opposite directions. If these go up by 1, this has to start one lower. Do you like how it looks? I don't. I'm sorry. One more rewrite. N equals 0 to infinity. Let's put n plus 1 and then 6 to the n, x to the n. Oh, that's stunning. Okay, how you feeling? You guys were almost there, only 7 more. I'm a little sad. Okay, so find a power series representation for the following function, ln of 1 plus x squared. I'm going to call this f of x. And if you remember from the power series made easy video, whenever there's a natural log, you actually start off by taking the derivative of this function. So f prime of x, derivative of ln 1 plus x squared, is 1 over 1 plus x squared. And then by the chain rule, we have to multiply by the derivative of what's inside. So that's 2x. Now let me find a power series representation for this function. So I want to rewrite the denominator as 1 minus something, which in this case is negative x squared. So my power series representation is going to be the sum n equals 0 to infinity, negative x squared to the n. And then since I have this extra 2x, I'm going to multiply by 2x. Good? Okay, so let's clean up. So f prime of x is 2x times the sum n equals 0 to infinity. This is negative 1 to the n, x to the 2n. And then that looks weird because we should bring this x inside the sum. So then this is 2 times the sum, n equals 0 to infinity, negative 1 to the n, x to the 2n plus 1. Good? Yay. Okay, so now I have a power series representation for f prime of x, but I want a power series representation for the original function that was given to me, f of x. So how do I get from the derivative to the original function? I take an antiderivative. I'm going to integrate. So f of x is going to be the integral of 2 times the sum, n equals 0 to infinity, negative 1 to the n, x to the 2n plus 1 dx. And no panic attacks. I know this looks very, very frightening, but just say to yourself, I'm integrating with respect to x. This is the only term that involves x. Everybody else is a constant, so you're not going to touch it. They're just going to come along for the ride and hang out. Okay, so just rewrite everybody else. That way you start writing something and the panic doesn't accumulate. And then you go, how do I take antiderivatives? I add 1 to the exponent and divide by the new exponent. So you're going to add 1, the exponent becomes 2n plus 2, and we divide by the new exponent, which is 2n plus 2. That's it, you guys. Look at you. We did take an antiderivative, so I have to put plus c. Okay, great. Now, how do I find c? Well, you look at where your power series is centered. In this case, it's just centered at 0. Remember earlier when we were finding radius of convergence and we had x minus a? So if you don't see plus or minus something, then it's just centered at 0. That means I'm going to substitute in 0 for x here and here to solve for c. So f of 0 is 2 times the sum. If x is 0, every single term is going to be 0. So I'm just summing up a bunch of zeros plus c. And what's f of 0? Well, f of x is ln of 1 plus x squared. So f of 0 would be ln of 1 plus 0. So ln of 1, which is just 0, is 2 times 0 plus c. So c is just 0, which it will be a lot of the time. Okay, so then if c is 0, I can simplify everything. This I don't need to keep anymore. I know it's just 0. And I have my power series representation. I can say f of x equals, I want you to be careful here because we can simplify. This is 2 times n plus 1, right? And then I can cancel now this 2 with the 2 down here. And just simply write everything as the sum, n equals 0 to infinity, negative 1 to the n, x to the 2n plus 2 over n plus 1. Good? Okay. Are we done? Should we box it? Well, remember I said, if possible, we want to leave it as x to the n, or in this case, what would look better, x to the 2n. So if I replace all of the n's with n minus 1 instead, 2 times n minus 1 plus 2, that's 2n minus 2 plus 2. Ooh, that would look good, because then that would just be x to the 2n. So what am I doing? If I make n become n minus 1, I'm subtracting 1 from all of these n's. So if those all go down by 1, this would need to start 1 higher. So then this is the same as the sum, n equals 1 to infinity. All of these go down by 1. So negative 1 to the n minus 1, x to the 2n, because when I replace n with n minus 1, don't forget to distribute, it just becomes 2n. And then in the denominator, n plus 1 goes down by 1, so now it's n. All right. Good, good. Let's look at another one. We have x squared times natural log of 1 plus 4x. So what I'm going to do actually, I know in the last one we had a natural log and we took the derivative right away. I don't want to do that because if I take the derivative here, I'm going to have to use the product rule and it's going to get oh so messy. So first let's find a power series representation for, I'm going to call g of x, ln of 1 plus 4x. So g prime of x would be 4 over 1 plus 4x, which I want you to think of it as 4 over 1 minus negative 4x, okay? So then that's 4 times the sum, n equals 0 to infinity, negative 4x to the n. So that's 4 times the sum, n equals 0 to infinity, negative 1 to the n, 4 to the n, x to the n. So then I can say now g prime of x is the sum, n equals 0 to infinity, negative 1 to the n. Bring this 4 to the first inside so they can not be so lonely. So 4 to the n plus 1, and then x to the n. Okay, good. So now I have a power series representation for the derivative of ln of 1 plus 4x. Let me, again, take the antiderivative so I can have a power series representation for ln 1 plus 4x. So g of x is going to be integral of the sum, n equals 0 to infinity, negative 1 to the n, 4 to the n plus 1, x to the n dx. No meltdowns. We're integrating with respect to x. That's the only term that involves x. So everybody just comes along for the ride. Don't touch a thing. N equals 0 to infinity, negative 1 to the n, 4 to the n plus 1. Add 1 to the exponent, and then you divide by the new exponent, and then don't forget plus c. Okay, and then we have here, this is g of x, which is ln 1 plus 4x. We need to find c, and we're going to do the same thing that we did last time. We're just going to substitute in 0 for x because that's where this series is centered. So that's going to make all of this just go to 0. So ln of 1 plus 4 times 0 is the sum of a bunch of zeros plus c. And ln of 1 is 0, so c is 0. Okay, cool. So then I can say g of x is the sum, n equals 0 to infinity, negative 1 to the n, 4 to the n plus 1, x to the n plus 1 over n plus 1. And this g of x is ln 1 plus 4x. Was that the function that they asked for originally? No, f of x also has an x squared multiplied in the front. So let me go ahead and do that. X squared times ln of 1 plus 4x. That's f of x. So that's going to be the sum, n equals 0 to infinity, negative 1 to the n, 4 to the n plus 1. If I multiply this by x squared, then we can simplify and combine those exponents. So that's x to the n plus 3 over n plus 1. Okay, now if we start at n equals 3, this will be x to the n, but then these will kind of be uglier. So I'm going to say it's up to you and your instructor if you want to simplify any more or leave it. You could start just at n equals 1 to infinity, and then this will be negative 1 to the n minus 1, 4 to the n, x to the n plus 2 over n. Or yeah, and that looks better, right, than what we had a second ago. I don't know, if you start at 3, then this will be n minus 2, n minus 2. I don't think I like that better. Let's just stop here. Tell me in the comments which one's your favorite. Do you want to start at 3? I don't think so. I think this is the cutest. This is the cutest. Okay, moving on. All right, we're still finding power series representations for these functions. And I actually haven't done one like this in that Power Series Made Easy video. But tan inverse of something, you treat the same way as when you see a natural log in the function. So I'm going to call f of x tan inverse of 4x. And let me go ahead and find a power series representation for tan inverse of 4x. And then I'll go ahead and multiply it by x to the 9th. Okay, so I'm going to start off by taking the derivative. Now, don't forget about your chain rule. That's right. Derivative of tangent something is 1 over 1 plus the something squared. And then by the chain rule, I have to multiply by the derivative of 4x, which is 4. So this is 4 over, let me rewrite this as 1 minus negative 16x squared, because I'm getting geared up to write a power series representation for this function. So we've got 4 times the sum, n equals 0 to infinity, negative 16x squared to the n. Okay, so I've got a power series representation for f prime of x. Let's clean it up though, it's kind of an ugly one. So f prime of x is 4 times the sum, n equals 0 to infinity. I can break this into 3 basic parts, negative, the 16, and then the x squared. So I'm going to write this as negative 1 to the n, 16 to the n, and then x to the 2n. And I do want to go ahead and bring this 4 inside with the 16. And you might think, that's a little peculiar. But remember, 16 I can write as 4 squared to the n. So this is the same as 4 to the 2n. And then if I bring this 4 inside, then I'll have 4 to the 2n plus 1. So that's perfect. So we have the sum now, n equals 0 to infinity, negative 1 to the n, 4 to the 2n plus 1, x to the 2n. And this is the power series for f prime of x. Okay, so same drill. I want power series for f of x, so I'm going to go ahead, anti-differentiate. So f of x is going to be integral of the sum, n equals 0 to infinity, negative 1 to the n, 4 to the 2n plus 1, x to the 2n dx. And then you ignore everybody except for x to the 2n. Everybody else is just a constant that comes along for the ride. So rewrite it exactly as is. Don't touch a thing. Okay, and then add 1 to the exponent because we're integrating. So it becomes x to the 2n plus 1 over 2n plus 1 plus c. And this power series represents f of x, which is tan inverse of 4x. And then I want to solve for c. So I'm going to substitute in x equals 0. That's where this power series is centered. That way every single term is 0. And then I have tan inverse of 4 times 0. Well, tan inverse of 0 is 0, right? And that's the sum of a bunch of zeros plus c. So again, c is 0. But check. Sometimes it's something else. It's not 0. So it's very worthwhile to do this step. Please don't take it for granted. Okay, so then f of x, or let me just say tan inverse of 4x. Tan inverse of 4x is the sum, n equals 0 to infinity, negative 1 to the n, 4 to the 2n plus 1, x to the 2n plus 1 over 2n plus 1. And then let's just compare. Are we done? Are we done? All I need is an x to the 9th. Ugh, I can do that. No big deal. Multiply by x to the 9th. Multiply by x to the 9th. And then we should be good. So then the function that they want, x to the 9th tan inverse of 4x, is the sum, n equals 0 to infinity, negative 1 to the n, 4 to the 2n plus 1, x to the 2n plus 10 over 2n plus 1. You can play around and try to shift the indices, but like if we can clean this up and make it just 2n, then these get more disgusting. So honestly, I would just leave it. Okay. And if you want to check your work, if you end up memorizing like the Maclaurin series for tan inverse of x, you can use that and manipulate it to come up with the power series representation for x to the 9th times tan inverse of 4x. So that's another way to check. Okay. Again, find power series representation for the following function. We have ln of 1 plus x cubed over 1 minus x cubed. I'm going to call this f of x. And remember, when we have a natural log, first we take the derivative, find a power series, then we integrate. Now, since I know I'm going to take a derivative, if I started differentiating right off the bat, I'd have a very nasty, nasty chain rule that would involve the quotient rule. I'm not going to do that because we've got a natural log. So let me use my natural log properties and rewrite this as ln 1 plus x cubed minus ln 1 minus x cubed. And now differentiating is going to become a lot more simple. So derivative ln 1 plus x cubed is going to be 1 plus x cubed in the denominator. And then by the chain rule, I have a 3x squared up top. Minus, and then derivative ln 1 minus x cubed would be 1 minus x cubed with a negative 3x squared up top. So then this ends up being positive, right? Good. Now, if you were to try to find a power series representation right now, you would have two series, one for each term, which is going to be a little messy to try to combine. It's doable, but what's even easier is actually if first I get a common denominator and write both of these as one term, and I will then only have to find one power series. And it's going to work out very nicely because notice the denominators are conjugate pairs. So I'm going to multiply this guy by 1 minus x cubed, top and bottom, and this one by 1 plus x cubed. Okay. So now I'm going to have 1 plus x cubed times 1 minus x cubed. And then we have 3x squared minus 3x to the 5th plus 3x squared plus 3x to the 5th. And 3x to the 5th cancels out. So we've got 6x squared over, notice the denominator becomes 1 minus x to the 6th. Beautiful. So we can easily find a power series representation for this function. So think of it as 6x squared times 1 over 1 minus x to the 6th. Power series for this guy is the sum, n equals 0 to infinity, x to the 6th to the n, and then just add a 6x squared. Are you all right? Okay, so f prime of x is going to be, let me leave the 6 out here, and then I have the sum, n equals 0 to infinity. This becomes x to the 6n plus 2. Okay, good. But I want power series representation for the original function, f of x. So we have to go ahead, take antiderivative of our power series that we have right now, dx. So you're going to add 1 to the exponent, divide by the new exponent, don't touch anything else. Just rewrite it calmly. So 6n plus 3 over 6n plus 3 plus c. Good? Okay. Now we can clean up a little bit because notice 6n plus 3, I can factor a 3 out, and then I have 2n plus 1. And if you want to think of bringing this 6 inside, it's going to cancel with the 3 and become a 2. So then now I have f of x is the sum, n equals 0 to infinity, 2 times x to the 6n plus 3 over 2n plus 1 plus c. Now we need to go find c. Again, this power series is centered at 0. f of 0 would be ln of 1, which is 0. So f of 0 equals 0. So c is 0. And then we're pretty much done now. So f of x is the sum n equals 0 to infinity, 2 times x to the 6n plus 3 over 2n plus 1. Stunning, stunning. Okay, next topic, use series to evaluate the limit. I have a whole separate video on this topic if you need a bunch of examples. But basically, you're going to look at the terms in the series, or in the limit, excuse me, and whatever has a nice Maclaurin series representation, we're going to replace it with the first few terms to help us evaluate the limit. Now, because they're telling me to use series to evaluate the limit, that's what I'm going to do. Otherwise, like, you could use L'Hopital's rule or something like that, and I do recommend you do so to check your answer, okay? So if you'll recall, our Maclaurin series for e to the negative 5x is the sum n equals 0 to infinity. It would be negative 1 to the n, 5 to the n, x to the n over n factorial. So let me list out the first few terms. It would be 1 minus 5x plus 5 squared x squared over 2 factorial minus 5 cubed x cubed over 3 factorial plus so on and so forth. So I'm going to replace this e to the negative 5x with all of this stuff, okay? So now we have the limit as x approaches 0. And just write out the first few and then put plus dot, 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 okay? So 1 minus 5x plus, this is 25x squared over 2 factorial minus 125x cubed over 3 factorial plus blah, blah, blah. And then we still have minus 1 plus 5x, and then this is all over x squared. And then usually these are written in such a way that stuff will cancel nicely. See, the 1 and the 5x. That's not a coincidence. Like someone sat here and wrote it, so that would happen, okay? So then now what do we have? We have the limit, x approaches 0. This is 25 over, you know what? Let me write it lower, and then I'll just put times 1 over x squared instead. So this is 25x squared over 2 minus 125x cubed over 6 plus blah, blah, blah times 1 over x squared. And now this 1 over x squared is going to distribute to everybody to infinitely many terms. And notice it's going to cancel so that the first term is now a constant. I'm just going to have 25 over 2 minus 125x over 6 plus a bunch more stuff, okay? Now, what's important is that all of the terms from here onward have x in the numerator. So we're taking the limit as x goes to 0. Every single term is going to go to 0. Every single term except 25 over 2, which is our answer. Okay, and then like I said, if you're nervous or you just want to check that you did all of these steps correctly, then you can take the limit and just apply L'Hopital's rule and make sure you get 25 over 2, okay? I wouldn't by choice do it this way unless I was instructed to do so. So just make sure you're paying attention to the directions. Okay, one more. We have the limit as x approaches 0 of cosine 4x minus 1 minus 8x squared over x squared. So cosine of 4x as a Maclaurin series would be 1 minus 4x quantity squared over 2 factorial plus 4x to the 4th over 4 factorial. This is why you do need to memorize those Maclaurin series that were on the table that I showed you earlier, because you use them here. Okay, so let's go ahead and replace cosine 4x with all of this here. So now I have the limit as x approaches 0. This is going to be 1 minus 16x squared over 2 plus, you know what? I don't feel like writing out what 4 to the 4th is. 4x to the 4th over 4 factorial minus 4x. And how many terms should you write? Enough so that you can see the pattern and what's going to cancel and evaluate the limit. Minus 1 minus 8x squared. Okay? Over x squared. And then just like last time, look. Oh, the 1 cancels. See? And then no, the 8x squared didn't cancel. This is negative 8x squared, and then that's another negative 8x squared. So I'm just going to combine like terms, right? Negative 8x squared minus another 8x squared. Now I have negative 16x squared. And I'm going to do the same thing as last time. I'm going to put times 1 over x squared over here. Okay, just so it makes things easier. Plus, this is 4 to the 4th, x to the 4th over 4 factorial minus 4 to the 6th, x to the 6th over 6 factorial plus blah, 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 times 1 over x squared. Good? And then, yep, same thing as last time. So this distributes through to everybody. And then usually like only a couple in the front will survive and the variable will cancel out entirely, right? So like negative 16x squared times 1 over x squared, that just becomes negative 16. And then I have plus 4 to the 4th x squared over 4 factorial minus 4 to the 6th x to the 4th. Everything's going down by 2 because we're canceling an x squared, plus a bunch more stuff. And then x is going to 0. So this term goes to 0, this term goes to 0, all the rest go to 0. The only one that doesn't is sweet little negative 16, which is our limit. And again, go back. If you're like, oh, I feel nervous, it's a test, my grade's on the line, just check using L'Hopital's rule, okay? All right, last two, find the sum of the series. Do you remember in part 1 at the very beginning, I said when you're asked to find the sum of the series, that's a very rare thing. It only happens if your series is geometric telescoping or a Maclaurin series. So here we have a Maclaurin series, right? And we need to recognize which function it represents so that we can come up with the sum. So you need to recognize, okay, if I were to write this in sigma notation, this is the sum, n equals 0 to infinity of 3 to the n over n factorial. Do you see that? This is 3 to the 0, 3 to the 1st, 3 squared, 3 cubed, 3 to the 4th, and then these are all n factorials. Well, who is this? Do you remember? E to the x is the sum, n equals 0 to infinity of x to the n over n factorial. So if you remember that, then you can go, oh, this is e raised to the, what's x in this case? The third. And that's it. Yeah, easy peasy lemon squeezy. My high school chem teacher used to say that. I loved her. Okay, last one, number 100. Oh my God, if you guys made it this far, comment what the answer is. And say, I made it to the end. I'm a survivor. 2/3 minus 2 cubed over 3 cubed, 3 factorial, plus 2 to the 5th over 3 to the 5th, 5 factorial. You see how all of the exponents are odd? Which Maclaurin series had all odd powers and was alternating and had factorials in the denominator? It was sine, right? Sine of x was the sum, n equals 0 to infinity, negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. So notice here the x is actually 2/3 because this series I could write it as the sum, n equals 0 to infinity, negative 1 to the n, 2/3 to the 2n plus 1 over 2n plus 1 factorial. So what's the sum? Sine of 2/3. You got it. Good job. Hopefully you commented that. If you didn't, comment it right now and say, I'm a survivor and I got sine of 2/3 with you, Professor V. So that's the 100th question. I hope this video was helpful. Don't forget to give it a thumbs up, subscribe if you haven't already, and follow me on Instagram and TikTok, Math with Professor V. Please let your friends and classmates know about my channel, help it grow so I can help more students learn calculus more easily. And I want to give you one last bit of advice about this whole unit. Students really freak out and get in their heads about it, but you guys, this can be a unit to make your comeback because a lot of Calc 2 builds on Calc 1 except for this unit. Sequences and series, you probably haven't even thought about them since pre-calc. And besides the integral test, you don't really use a lot of your calculus skills. I mean, you do limits extensively, but it's not like you have to do trig sub and this and that and arc length and all of the things that might be really giving you a rough time. So think of it as, hey, this is a brand new unit. It's a little different than what I'm used to studying in calculus, but it's almost like a level playing field. Use this unit to make a strong comeback and bring your grade up. Don't let it intimidate you. Explain it to other people, re-explain it to yourself out loud. It doesn't matter if you look crazy. It's helpful to reinforce the concepts because once it clicks and you will be loving it. So I love sequences and series. I hope it's helping you and that comes across in the video that you guys can master this. All right. Please leave me a comment down below and I will be back sooner than later. I love you guys so much. Bye.